Newton's first law. Newton's first law, also called the law of inertia, explains that an object will keep moving in a straight line at the same speed or stay at rest unless a force acts on it. Motion does not change on its own. Key terms include force, mass, velocity, and inertia. Inertia is the tendency of an object to resist changes in its motion. The law states that objects at rest remain at rest, and objects in motion continue moving at a constant velocity unless acted upon by an external force. This means that motion requires no effort to maintain. Forces are needed only to start, stop, or change the direction of movement. A ball on the ground stays still until kicked. A moving car stops only when brakes are applied. Satellites keep moving in space without engines. Applies best when friction or air resistance is negligible. Applicable across systems. Inertia teaches that systems resist change and energy is needed to alter motion. Speed versus velocity. Speed measures how fast an object moves, a scalar quantity without direction. Velocity measures how fast and in which direction an object moves, a vector quantity. Velocity is displacement divided by time. Speed is distance divided by time. Uniform motion implies constant speed or velocity. Speed tells how quickly distance changes. Velocity tells both how quickly and in which direction displacement changes. Velocity can be negative if motion reverses. A car moving 60 km per hour shows speed. A car moving 60 km per hour east shows velocity. Athletes use speed. Pilots use velocity for navigation. Speed cannot indicate direction. Velocity requires knowing direction. Both assume straight-line motion for simple calculation. Applicable across systems. Always consider direction when analyzing motion. Scalar and vector views together give complete understanding. Velocity changes if direction changes even at constant speed. Acceleration. Acceleration is the rate at which an object's velocity changes over time. It tells us how quickly something speeds up, slows down, or changes direction. Velocity, speed, time, force, and mass are closely connected. Acceleration depends on how fast velocity changes in a certain time. Newton's second law explains acceleration. It states that the acceleration of an object equals the net force acting on it divided by its mass. Acceleration shows how motion changes. Positive acceleration means speeding up, negative means slowing down, and changing direction is also a form of acceleration. A car starting from rest, a ball dropped from height, or a cyclist pressing harder on pedals all experience acceleration. Acceleration assumes a constant mass and does not consider air resistance or friction unless included in force. Acceleration connects force and motion. Observing it helps predict outcomes, design vehicles, and understand nature's patterns. Newton's second law. Newton's second law explains how objects move when a force acts on them. It shows that an object's acceleration depends on the force applied and its mass. Key terms include force, mass, and acceleration. Force is a push or pull. Mass is the amount of matter in an object. Acceleration is the rate at which an object's speed changes. The law can be written as F equals m times a, meaning force equals mass multiplied by acceleration. A heavier object needs more force to move the same way as a lighter object. The greater the force, the faster an object accelerates. Pushing a bicycle, launching a rocket, or kicking a ball demonstrates this law in daily life. It applies only when forces are measured in straight lines, and the object is not at very high speed. It teaches that effort must match resistance, and that motion depends on both force and mass. Distance is the total path traveled by an object regardless of direction. Displacement is the straight line from the starting point to the ending point, with a specific direction. Distance follows the principle of scalar measurement. Displacement follows the vector principle, having both magnitude and direction. Distance tells how much ground is covered. Displacement shows how far and in what direction an object has moved from its initial position. Walking around a park for 10 minutes may cover 800 meters of distance, but if you return to the start, displacement is zero. In physics, displacement helps in calculating velocity and acceleration. Distance can never be negative. Displacement can be zero even when distance is positive. Displacement requires reference points and direction. Applicable across systems. Always consider the path versus the net change. Distance measures effort. Displacement measures result. In real life and science, both offer different insights. Newton's third law states that for every action, there is an equal and opposite reaction. This means that forces always come in pairs, acting on two different objects. When one object exerts a force on another, the second object pushes back with a force of the same strength, but in the opposite direction. The magnitudes are equal, directions are opposite, and they act on separate bodies. This law explains why movement happens. A force alone cannot exist without a counterforce. Action and reaction are simultaneous and inseparable. A swimmer pushes water backward and moves forward. A rocket expels gas downward and rises. Jumping off a boat pushes the boat backward. It applies only to interactions between objects, not to forces on a single object alone. Every force has a response, reminding us that interactions are mutual and balance exists in nature. Mass is the amount of matter contained in an object. Weight is the force exerted by gravity on that mass. Mass does not change with location. Weight changes depending on the strength of the gravitational field. Mass is governed by the law of inertia. Weight is governed by Newton's law of universal gravitation, and the formula weight equals mass times gravitational acceleration. Mass measures how much matter is present. Weight measures how strongly gravity pulls on that matter. A heavy object can have the same mass as a light object on a different planet because weight depends on gravity. A person weighing 60 kilograms on Earth weighs less on the Moon. Mass of a car stays constant everywhere. Weight varies with location. Mass is constant under normal conditions. Distinguish between intrinsic properties like mass and forces like weight when solving physics problems. Always account for gravity when calculating weight. Gravity near Earth is the force that pulls objects toward the center of the Earth. It gives weight to everything around us and keeps us grounded. Without gravity, we would float into space. The strength of gravity is described by Newton's law of universal gravitation. Near Earth, it is often simplified as a constant acceleration of 9.8 meters per second squared. Gravity explains why objects fall when dropped and why planets orbit the Sun. It acts on all masses, attracting them toward each other, but near Earth, the planet's mass dominates. A falling apple, a rolling ball, and the motion of satellites are all shaped by gravity. Engineers account for gravity when designing buildings, bridges, and roller coasters. Gravity's strength weakens with distance from Earth. Other forces like air resistance can affect falling objects. Gravity teaches that every object attracts every other object and that natural forces are predictable and consistent, guiding movement and structure in all systems. Friction is a force that resists motion when two surfaces touch each other. It can slow down or stop moving objects and is always present in everyday life. Friction depends on the nature of the surfaces and the force pressing them together. The frictional force is proportional to the normal force and is described by the equation F equals μn, where mu is the coefficient of friction. Friction converts motion into heat and prevents slipping. It is the invisible grip that allows walking, driving, or holding objects without sliding. Friction helps brakes stop a car, a pencil write on paper, and shoes grip the ground. It is useful in machines, but can also cause wear. Friction cannot be avoided completely. Too much friction slows machines, while too little causes slipping. Friction teaches balance between resistance and motion. Designing surfaces requires understanding when to increase or reduce friction to achieve control and safety. Work is done when a force is applied to an object and the object moves in the direction of the force. It is a way of transferring energy from one body to another. The amount of work done is calculated as the product of the force and the distance moved in the direction of the force. If the force and movement are not in the same direction, only the component of force along the movement counts. Work measures how much energy is used to move an object. Positive work adds energy, while negative work removes energy from the system. Lifting a book, pushing a cart, or pulling a rope are common examples of work. Machines like pulleys help reduce the effort needed. No work is done if the object does not move or if the force is perpendicular to the motion. Applicable across systems. Energy cannot be created or destroyed. Work always involves force and displacement, teaching the importance of direction and effort in any task. Kinetic energy. Kinetic energy is the energy an object has because of its motion. Any moving object, whether it is a rolling ball or flowing water, carries this energy. The kinetic energy of an object depends on its mass and the square of its speed. It is calculated using the formula K equals half mass times velocity squared. Kinetic energy represents the ability of a moving object to do work. The faster or heavier the object, the more energy it possesses. A speeding car, a flowing river turning a water wheel, and a thrown stone all demonstrate kinetic energy in action. Engineers use this idea to design safer vehicles and efficient machines. Kinetic energy only applies when objects are moving relative to a reference point. It does not exist for objects at rest. Energy is conserved, and understanding motion helps predict how energy transfers across systems. Potential energy is the energy stored in an object because of its position or arrangement. It is the energy that an object has the potential to release when conditions change. For example, a rock perched on a hill has energy ready to become motion if it falls. The law of conservation of energy explains that energy cannot be created or destroyed. Potential energy can change into kinetic energy and back, but the total energy remains constant. Potential energy represents the capacity to do work. A stretched spring or lifted book carries energy that can make things move when released. Water behind a dam, a drawn bow, or a raised swing all store energy that can perform actions. Potential energy depends on reference points, forces, and positions. It only exists while the object is in a state to change. Observe positions and arrangements carefully because they hold hidden energy. Energy is transferable and shapes motion in all systems. Conservation of energy. Conservation of energy means energy cannot be created or destroyed. It can only change from one form to another. The total energy in a closed system remains constant. Energy can be in the form of motion, heat, light, or stored energy like in a stretched spring or fuel. The law of conservation of energy states that the total energy of an isolated system is constant. Energy lost in one form appears in another form. When a ball falls, its potential energy decreases while its kinetic energy increases. The total energy of the ball and earth system remains unchanged. Energy transfers, but the sum stays the same. Rubbing hands produces heat from motion. Cars convert chemical energy of fuel into motion. Plants convert sunlight into chemical energy. Applies to closed systems. Energy can leave or enter an open system. Energy efficiency, careful planning, and understanding transformations help us use energy wisely. Momentum is the measure of how much motion an object has. It depends on the mass of the object and its velocity. A heavier object moving fast has more momentum than a lighter object moving at the same speed. Momentum follows the law of conservation. This means the total momentum of a closed system remains constant unless acted upon by an outside force. Momentum represents the difficulty of stopping a moving object. The larger the momentum, the harder it is to change its motion. A rolling ball continues to move because it has momentum. Cars, rockets, and even athletes use momentum to move efficiently. In collisions, momentum helps predict the result of impacts. Momentum conservation works only in isolated systems with no external forces, like friction or air resistance. Understanding momentum teaches us balance, control, and the effect of mass and speed in motion. Impulse is a concept in physics that describes the effect of a force acting on an object over a period of time. It measures how much a force changes an object's motion. Impulse is governed by the impulse-momentum theorem. It states that the impulse on an object equals the change in its momentum. Mathematically, impulse equals force multiplied by time. Impulse explains how forces over short or long times affect motion. A strong force for a short time or a small force for a long time can both change momentum. Hitting a baseball, kicking a football, or using airbags in cars all involve impulse. Sports, transportation, and safety devices rely on this concept. Impulse applies when the force and time interval are measurable. Very complex forces, or extremely short times, may need approximations. Applicable across systems. Understanding impulse teaches us that timing and force together determine motion changes in many systems, from vehicles to sports. Simple machines are devices that make work easier by changing the direction or magnitude of a force. They do not create energy, but help humans perform tasks more efficiently. Examples include levers, pulleys, inclined planes, screws, wedges, and wheels and axles. Simple machines operate under the principle of mechanical advantage. The work input equals the work output if friction is ignored. Force multiplied by distance on one side equals force multiplied by distance on the other side. They allow a smaller force to move a larger load by increasing the distance over which the force is applied. This explains why lifting a heavy object with a lever feels easier. A seesaw, a pulley system to lift water, a ramp to load goods, and a screw in a jar lid. Friction reduces efficiency. They cannot multiply energy, only redistribute it. Applicable across systems. Work can be simplified by changing direction or distance of force. Efficiency requires balance between effort and load. Pressure is the force applied per unit area. It tells us how much force acts on a surface. When we push a finger on a balloon, we feel pressure because the force spreads over the area of contact. Pressure follows the formula P equals F divided by A, where F is the applied force and A is the area. In fluids, pressure increases with depth and is transmitted equally in all directions, known as Pascal's principle. Pressure shows how concentrated a force is. A needle pierces cloth easily because the force is over a tiny area, creating high pressure. A broad hand pushes gently due to low pressure over a large area. Car tires, hydraulic lifts, syringes, and submarines all use pressure. It helps lift, squeeze, or measure forces safely. Pressure is meaningful only where force acts on a surface. It varies with area and medium. Pressure teaches that spreading force reduces its effect, while concentrating force increases impact. Observing pressure guides design and safety. Archimedes' principle. Archimedes' principle explains how objects behave in fluids. It states that when an object is partially or fully submerged in a liquid, it experiences an upward force called buoyancy. This force pushes the object upward, making it feel lighter. The upward buoyant force is equal to the weight of the liquid displaced by the object. This law connects the object, the fluid, and the force acting on it. The principle shows that fluids resist objects trying to push through them. The denser the fluid, the stronger the buoyant force. Objects float if this force is greater than their weight. Ships float because they displace enough water to balance their weight. Hot air balloons rise as the air inside is lighter than outside air. Submarines adjust buoyancy to dive or surface. Archimedes' principle works only in fluids at rest. It does not account for moving fluids or surface tension effects. The principle teaches balance between forces, helping us understand floating, sinking, and designing objects in fluids. Density is a measure of how much mass is contained in a given volume of a substance. It tells us how tightly matter is packed together. A denser object has more matter in the same space compared to a less dense one. The formula for density is mass divided by volume. This simple relationship allows us to calculate density for solids, liquids, and gases. Density explains why some objects float while others sink. An object floats in a fluid if its density is less than the fluid's density. Iron sinks in water because it is denser than water. Oil floats on water because it is less dense. Airplanes and ships rely on density differences to stay afloat. Density changes with temperature and pressure. It is not constant for gases under varying conditions. Understanding density helps predict material behavior, design objects, and explore natural phenomena in everyday life. Heat is the energy that flows from a hotter object to a cooler one. Temperature measures how hot or cold an object is. Heat depends on the amount of substance, while temperature does not. Heat flow follows the second law of thermodynamics. Temperature follows the Zeroth law of thermodynamics, which allows comparison of thermal states. Heat shows energy transfer, like when a spoon warms in hot tea. Temperature indicates the intensity of thermal energy, like how hot the tea feels. Boiling water transfers heat to a pan. Fever indicates high body temperature. Thermal engines convert heat to work. Heat cannot be measured directly. It is inferred by energy change. Temperature readings are valid only in thermal equilibrium. Applicable across systems. Energy flows from high to low temperature. Knowing both heat and temperature helps predict changes in everyday and industrial systems. Thermal expansion is the tendency of matter to change its size or volume when its temperature changes. When materials are heated, their particles move faster and spread apart, making the material expand. Cooling has the opposite effect, causing contraction. The expansion of most solids, liquids, and gases can be described by the formula change in length equals original length times coefficient of linear expansion times change in temperature for solids. Similar principles apply for volume changes in liquids and gases. Thermal expansion explains why bridges have gaps, railway tracks are laid with spaces, and liquids rise in thermometers. It shows how heat energy affects particle motion and distances between them. Railway tracks, overhead power lines, thermometers, and hot air balloons all use thermal expansion practically. Extreme temperatures may cause material deformation or breaking beyond predictable expansion. Understanding thermal expansion helps design safer structures and machines that can handle temperature changes effectively. Matter exists in different forms known as states. The three common states are solid, liquid, and gas. Solids have fixed shape and volume. Liquids take the shape of their container, but have fixed volume. Gases have neither fixed shape nor fixed volume, and expand to fill their container. The behavior of matter in different states is governed by particle theory. Particles are in constant motion, and the energy they possess determines the state. Increasing temperature increases particle motion, while decreasing temperature slows it down. Solids have closely packed particles vibrating in place. Liquids have particles that move freely but stay close. Gases have particles moving rapidly and far apart. Changes of state occur when energy is added or removed. Ice melting, water boiling, oxygen and air. Extremes of pressure and temperature can form plasma or Bose-Einstein condensates. Energy controls motion. Matter adapts its form according to energy and environment. Reflection of light occurs when a beam of light strikes a surface and bounces back. This is why we can see objects in a mirror or notice our image in calm water. The process follows the law of reflection. The angle at which light hits a surface, called the angle of incidence, is equal to the angle at which it leaves the surface, called the angle of reflection. Reflection helps explain why we see shapes, colors, and movements of objects. Smooth surfaces give clear images, while rough surfaces scatter light, producing diffuse reflection. Mirrors, polished metals, camera lenses, and periscopes all use reflection. Even sunlight bouncing off a lake illustrates this principle. Reflection is most clear on smooth, shiny surfaces. Rough or dark surfaces reduce clarity. Reflection shows that predictable rules govern nature. Observing carefully helps understand light behavior and its interaction with different surfaces. Refraction of light is the bending of light when it passes from one transparent medium to another. Light changes its speed as it enters a different material, which causes it to change direction. The law that governs refraction is called Snell's law. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a pair of media. Refraction shows that light does not always travel in a straight line. Its speed depends on the medium, and the bending effect can make objects appear shifted from their real position. A straw in a glass of water looks bent. Lenses in glasses and cameras use refraction to focus light. Prisms separate white light into colors. Refraction occurs only at the boundary of two transparent media and requires light to change speed. Refraction teaches that change in environment alters motion and perception, a principle seen in many natural and technological systems. Ohm's law describes the relationship between voltage, current, and resistance in an electric circuit. It states that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance. The law is written as V equals I times R, where V is voltage, I is current, and R is resistance. This simple formula helps us calculate one quantity if the other two are known. Voltage pushes the electrons through the conductor, resistance slows them down, and current measures the flow of electrons. A higher voltage produces more current if resistance remains the same. It is used in designing electric circuits, charging batteries, and powering devices safely. It applies only to ohmic materials where current changes linearly with voltage, and does not work for nonlinear components like diodes. Applicable across systems. Understanding cause and effect, balance, and proportional relationships helps in analyzing many physical and real-world systems. Projectile motion is the movement of an object that is thrown or launched into the air and moves under the influence of gravity. The object follows a curved path called a trajectory. Its motion combines horizontal movement at a constant speed and vertical movement influenced by acceleration due to gravity. A projectile has key properties such as initial velocity, angle of projection, and acceleration due to gravity. Its horizontal motion is uniform, while vertical motion is accelerated. Maximum height, time of flight, and range are important traits that define its path. The motion can be analyzed by breaking it into two perpendicular components, horizontal and vertical. The horizontal component depends on initial speed and time, while the vertical component depends on gravity and time. Both components work together to form the parabolic trajectory. The projectile rises until vertical velocity becomes zero, then descends under gravity. Horizontal velocity remains constant. Changing the launch angle or speed affects the height, range, and time in the air. Air resistance can slightly alter the path, but is often neglected in basic analysis. Projectile motion is recognized by observing objects like a thrown ball, an arrow in flight, or water from a fountain. Understanding its motion requires visualizing separate horizontal and vertical effects acting together. It is a part of classical mechanics and influences fields like sports, engineering, and space science. Predicting trajectories helps in aiming, launching, or designing objects for flight. The trajectory is always parabolic in the absence of air resistance. Time of ascent equals time of descent. Maximum range occurs at a 45-degree launch angle. Similar projectiles show consistent relationships among speed, angle, and distance. Projectile motion demonstrates how forces shape movement. It teaches the value of analyzing complex actions in simple components. It shows the predictable nature of physical laws and encourages curiosity about motion in the world around us. Uniform circular motion is the motion of an object moving along a circular path with constant speed. The fundamental idea is that although the speed remains constant, the direction of motion continuously changes, creating acceleration toward the center. The essence is the balance between inertia trying to move the object straight and a central force pulling it inward. Key traits include constant speed, changing velocity, and centripetal acceleration directed toward the circle's center. It exists whenever an object moves in a circle under a central force. The radius, speed, and period of rotation are interconnected, determining the strength of the inward force needed to maintain motion. The structure involves the circular path, the object in motion, and the center as a reference. Elements connect through relationships such as speed influencing period and centripetal force linking mass, radius, and velocity. The motion forms a continuous loop, each point dependent on the central pull. The motion evolves with changes in speed, radius, or mass. Faster speeds increase the required inward force. Larger radii reduce it. Sequences show that for one complete rotation, velocity direction changes smoothly, creating a dynamic system of acceleration and motion. Recognizing uniform circular motion involves observing constant speed along a curved path and inward acceleration. Context matters, as motion can appear uniform from certain perspectives while forces remain hidden. This motion exists within mechanical systems, planetary orbits, and everyday devices like car wheels or fans. It influences stability, rotation, and energy transfer in larger systems. The motion is periodic, repeating each cycle at a regular interval called the period. Predictable outcomes include repeating positions, velocity directions, and centripetal forces. Uniform circular motion shows how forces control direction and speed, teaching principles of balance, acceleration, and periodicity. It illustrates the connection between motion, force, and energy across natural and engineered systems. Centripetal force is the force that keeps an object moving in a circular path. Whenever something turns around a circle, it needs a pull directed toward the center of the circle. Without this inward pull, the object would fly off in a straight line. The essence of centripetal force is that it constantly changes the direction of motion without changing the speed, guiding the object along its circular path. Centripetal force always points toward the center of the circle. It depends on the mass of the object, its speed, and the radius of the circle. If the object moves faster, the force must be stronger. It exists as tension in a string, gravity in planetary orbits, or friction on a car turning a curve. All components, like mass, velocity, and radius, work together to maintain circular motion. The framework of centripetal motion links mass, velocity, and radius through the formula F equals mv superscript 2/r. Each element affects the others. The faster the object or the smaller the radius, the greater the force needed. The inward force and the circular path are always connected. Centripetal force changes if speed or radius changes. Increasing speed increases the inward force required. If the radius grows, less force is needed. The force constantly adjusts to keep the object on the path. We can see centripetal force in action when a car turns a corner, a swing spins, or the moon orbits Earth. It is recognized by the constant inward pull needed to maintain circular motion. Centripetal force is part of motion systems and affects satellites, amusement park rides, and planetary orbits. Its influence extends to all objects moving along curved paths. The force always points inward. Speed and radius determine its size, and predictable motion follows circular paths. Centripetal force teaches that motion requires balance between direction and speed. It shows how invisible forces guide objects, offering insight into both natural and human-made systems. Torque is the measure of how much a force acting on an object causes it to rotate around an axis. Imagine trying to open a door. Pushing near the handle creates more rotation than pushing near the hinges. This twisting effect is the essence of torque. It depends on the strength of the force and the distance from the point of rotation. Torque has magnitude and direction. It acts around an axis, either clockwise or counterclockwise. Its size grows with a stronger force or a longer lever arm. Torque is linked to rotational motion, showing how forces and distances work together to produce turning effects. Torque connects force, lever arm, and axis of rotation. The lever arm is the line from the axis to where the force is applied. Forces at different angles create different torque. The pattern is simple. More force or farther from the pivot produces stronger rotation. Torque changes with the applied force or position. Pushing harder or farther from the pivot increases rotation. Balanced torques keep objects still, while unbalanced torques cause motion. It can speed up or slow down rotation depending on how forces interact. Torque is seen in doors, wrenches, seesaws, and car wheels. Understanding torque helps predict rotation. Its effect is relative. The same force feels stronger or weaker depending on where it is applied. Torque affects mechanical systems, engines, and simple tools. It influences motion, stability, and energy transfer. It is central to machines that rotate or turn objects. Torque often appears in predictable ways. Longer levers and stronger forces repeatedly create stronger rotation. Balanced torques result in no motion, showing recurring stability patterns. Torque teaches how force and distance work together. It is a guiding principle for design, engineering, and daily activities. Recognizing torque helps explain motion in machines and nature alike. Rotational kinematics. Rotational kinematics studies how objects rotate around an axis. It explains the motion of spinning wheels, turning fans, and planets orbiting the sun. The main idea is to understand how angular position, angular velocity, and angular acceleration describe rotation over time. It shows how motion in a circle differs from motion in a straight line. Rotation involves angles, not distances. Angular velocity measures how fast something spins, while angular acceleration measures how that speed changes. The direction of rotation follows the right-hand rule. Every point on a rotating object moves along a circular path, but the speed depends on its distance from the center. Rotational motion uses formulas similar to linear motion but replaces distance with angle, speed with angular velocity, and acceleration with angular acceleration. Equations connect these elements to predict the future position or speed of a rotating object. Angular displacement, velocity, and acceleration are linked just like position, speed, and acceleration in straight motion. A wheel spinning faster shows positive angular acceleration. A figure skater pulling arms and speeds up rotation because angular momentum is conserved. Objects can rotate uniformly or with changing speed, and interactions like friction and torque affect rotation. Rotation is observed in everyday life. Watching a spinning bicycle wheel or turning doorknob gives an intuitive sense of rotational motion. Measurement tools like protractors or tachometers quantify it. Rotational motion connects to engineering, astronomy, and mechanics. It influences gears, engines, and satellite orbits. Rotating systems often show periodic behavior, returning to initial positions. The time for one full rotation is called the period, and frequency counts rotations per second. Understanding rotational kinematics helps explain natural and man-made phenomena. It guides design of machines, sports techniques, and space travel, showing how circular motion shapes our world. Moment of inertia is the measure of an object's resistance to rotational motion. It depends on the distribution of mass around an axis. The farther the mass is from the axis, the harder it is to spin. Imagine a spinning door. The wider the door, the more effort needed to push it. It is influenced by the shape, mass, and axis of rotation. A solid disk and a hollow ring of the same mass rotate differently because their mass is spread in different ways. Moment of inertia can be summed for multiple parts of a system, showing how each part contributes to overall resistance to rotation. Objects have axes around which they rotate. The moment of inertia is calculated relative to these axes. For simple shapes like rods, cylinders, and spheres, formulas exist. Complex objects are divided into smaller elements, each with its own contribution. These contributions combine to give the total moment of inertia. When a force acts on a rotating object, the moment of inertia determines how quickly it accelerates. A heavy flywheel spins slowly at first, but resists changes once moving. If mass shifts closer to the axis, rotation becomes easier, showing how distribution affects motion. It can be recognized in everyday life. Swinging a bat, spinning a wheel, or riding a merry-go-round all demonstrate the concept. Understanding moment of inertia helps predict how objects respond to forces. It influences engineering, sports, and machinery. Large structures, wheels, and rotating arms rely on precise calculations to ensure stability and efficiency. Objects with mass far from the axis consistently resist motion more. Rotational motion often follows predictable paths depending on inertia. Moment of inertia teaches how mass distribution affects motion. It guides design, safety, and energy efficiency. Recognizing its role helps us connect everyday actions with fundamental physical laws. Angular momentum is the measure of how much rotational motion an object has. It tells us how fast something spins and how difficult it is to stop. The principle is based on the idea that spinning objects resist changes in their rotation, just like moving objects resist changes in straight motion. Angular momentum depends on the mass of the object, how far it is from the axis of rotation, and how fast it spins. It exists in rotating objects like wheels, planets, or ice skaters. Each part of a spinning object contributes to the total momentum. Changing one component changes the whole system. Objects rotate around an axis, and each particle of the object has its own tiny rotational contribution. Together these form a complete angular momentum. The parts are connected, and their motions combine following the rules of rotation. Angular momentum stays the same if no outside force acts. When a figure skater pulls in her arms, she spins faster. This shows the momentum can change speed, but is conserved overall. Rotational motion adapts to changes in shape or distribution. Angular momentum is recognized in spinning objects or orbiting planets. Observing faster or slower rotations gives clues about changes in momentum. Context like size, shape, and spin rate helps us interpret its effects. It is part of mechanics and influences other motions. Planetary rotations, spinning wheels, and even molecules show angular momentum. It connects micro and macro systems. Rotating systems follow patterns. Spinning faster when mass moves closer or slower when it spreads out is predictable. These tendencies appear in sports, astronomy, and engineering. Understanding angular momentum helps explain the universe. It guides engineers in machines, athletes in motion, and scientists in celestial paths. It teaches that motion, even spinning, has rules that shape the world. Amplitude is the measure of the maximum extent of a vibration or oscillation. It represents how strong or intense a wave is, whether it is sound, light, or a wave in water. Essentially, amplitude tells us how much energy the wave carries. Amplitude is seen as the height of a wave from its resting position. Larger amplitude means a taller wave and more energy, while smaller amplitude means a gentler wave. It can be measured in units, like meters for mechanical waves or volts for electrical waves. Amplitude relates closely to wave frequency and wavelength, but it is independent of the wave's speed. Waves are structured with peaks and troughs. The amplitude exists as the distance from the centerline to a peak. All waves follow a pattern where amplitude, frequency, and wavelength work together to form the complete wave system. Changes in one part of the wave can influence perception of amplitude. Amplitude can grow or decay depending on energy input. For example, a swing pushed harder swings higher, increasing amplitude. Over time, friction or resistance reduces amplitude. Interactions within wave systems, such as interference, can combine or cancel amplitudes. We perceive amplitude in many ways. Loud sounds have high amplitude, while soft sounds have low amplitude. Bright light has high amplitude, while dim light has low amplitude. Context matters, as the same amplitude may feel different depending on surrounding conditions. Amplitude exists in many systems, from oceans to sound waves to electrical signals. It affects energy transfer, signal strength, and intensity. Its influence extends to everyday experiences like music, light, and even the motion of objects. Amplitude often follows predictable patterns. Repeating waves maintain a constant amplitude unless energy is added or lost. Certain systems show rhythmic increases and decreases, like tides or vibrating strings. Amplitude helps us understand energy and intensity in the world. Recognizing it allows us to predict wave effects, measure signals, and control systems efficiently. It is a guide to seeing the hidden power in simple movements. Gravitation is the natural force by which all objects with mass attract each other. It is the invisible thread that holds planets, stars, and galaxies together. At its essence, gravitation explains why objects fall toward the Earth and why the planets orbit the Sun. It is a universal interaction that operates across the cosmos. Gravitation is always attractive and acts between any two masses. Its strength depends on the mass of the objects and the distance between them. The larger the mass, the stronger the pull. The farther apart the objects are, the weaker the force. This force acts at a distance without any physical contact. Gravitational interactions are structured through systems like planets around a star or moons around a planet. Each object follows a path determined by the combined pulls of surrounding masses. This network of attractions creates organized orbits and stable formations within space. The force of gravitation changes with position and motion. Objects accelerate toward each other as they get closer. Orbits can be circular or elliptical depending on the balance between speed and gravitational pull. Over time, gravitation shapes planets, stars, and even galaxies through continuous attraction. Gravitation is recognized through falling objects, tides, and orbital movements. It can be measured using instruments like gravimeters. Observing how objects move allows humans to understand the invisible influence of this force. Gravitation affects everything from tiny particles to massive celestial bodies. It governs planetary motion, star formation, and the structure of the universe. Its reach is limitless across space. Objects under gravitation often follow predictable paths. Orbits repeat, tides rise and fall, and planets maintain regular cycles around stars. These patterns reveal the consistency of gravitational rules. Gravitation teaches that unseen forces govern visible motion. It connects the smallest pebble to the largest galaxy and guides exploration, discovery, and understanding of the universe. Escape velocity is the speed an object must reach to break free from the gravitational pull of a planet or celestial body without further propulsion. It is not about moving fast for a short time, but having enough energy to overcome gravity completely. Imagine a rocket trying to leave Earth. It must reach this critical speed to move into space. The underlying principle is the balance between kinetic energy and gravitational potential energy. Escape velocity depends on the mass and radius of the celestial body. Larger planets have stronger gravity, so higher speeds are required. It exists as a specific value for each body and is independent of the object's mass. Components like the gravitational constant, planet mass, and radius are mathematically related to determine this speed. The concept connects kinetic energy, potential energy, and gravity. The formula shows how these elements interact. Escape velocity organizes energy requirements for leaving a planet, linking speed, mass, and distance from the center. Patterns emerge in how heavier planets demand higher velocities. Escape velocity does not change with the object's motion once reached, but it varies with altitude. As you move away from the planet, less speed is needed. Interactions include forces acting on the object and how energy converts from motion to overcoming gravity. It can be understood through simulations or rocket experiments. Context matters. On Earth it is about 11.2 kilometers per second, but on the Moon it is much lower, showing that gravity defines the experience of escape. Escape velocity affects space missions, satellite launches, and planetary science. Its influence extends to energy calculations, orbital mechanics, and engineering decisions. Stronger gravity means higher escape velocity, a consistent pattern across planets. Predictable outcomes arise in rocketry and astrophysics whenever gravitational escape is considered. Escape velocity teaches the relationship between energy, gravity, and motion. It guides our understanding of space travel and the forces that shape planetary systems, showing how precise calculations allow humanity to explore beyond Earth. Simple harmonic motion is a type of motion in which an object moves back and forth repeatedly around a central position. The movement happens in a smooth, regular rhythm. The essential principle is that the restoring force is always directed toward the equilibrium position and is proportional to the displacement. Think of a pendulum swinging or a spring bouncing up and down. The main traits include periodicity, meaning the motion repeats after a fixed time. The amplitude is the maximum distance from the center, and the frequency shows how often the motion repeats in 1 second. The phase represents the position of the object at a particular time. These characteristics work together to create predictable patterns of motion. The structure of simple harmonic motion relies on the relationship between force, mass, and acceleration. In a spring mass system, the spring applies a force proportional to how far the mass is pulled or pushed. In a pendulum, gravity provides the restoring force. These elements interact continuously, producing regular oscillations. Objects in simple harmonic motion change their position smoothly over time. Velocity is highest at the center and zero at the extremes. Acceleration is greatest at the extremes and zero at the center. The energy shifts between kinetic and potential forms, creating continuous motion. Simple harmonic motion can be recognized by its regular back and forth movement. Observing a swinging swing, a vibrating guitar string, or a bouncing spring helps understand the pattern. Context determines whether we see it as fast or slow, small or large. It appears in mechanical systems, sound waves, and even light vibrations. Its influence extends to designing clocks, musical instruments, and engineering structures. The motion is highly regular. One cycle repeats exactly like the previous one. Time period and frequency are constant, creating predictable sequences. Simple harmonic motion teaches the value of balance and rhythm. It shows that forces and motion are interconnected. Understanding it helps in science, engineering, and everyday observation of natural phenomena. A spring mass system is a simple mechanical system made up of a mass attached to a spring. The fundamental idea is that the spring can stretch or compress, and the mass moves back and forth. The underlying principle is Hooke's law, which states that the force exerted by the spring is proportional to its displacement. This system is a basic example of oscillatory motion. The system has essential traits such as elasticity of the spring and inertia of the mass. The spring stores energy when stretched or compressed and releases it to move the mass. The mass resists motion due to its inertia. These components are connected, and the balance between spring force and mass motion defines the system's behavior. The structure is simple. A mass hangs from a spring or sits on a horizontal surface with the spring fixed at one end. The spring and mass form a loop of energy exchange. The arrangement ensures that stretching or compressing the spring causes the mass to oscillate, showing a clear pattern of interaction. The system moves in repeating cycles called oscillations. When displaced, the mass accelerates toward the equilibrium point. Energy shifts between potential energy in the spring and kinetic energy of the mass. Over time, damping can slow the motion, creating smaller oscillations until the system stops. We can recognize the system by observing repetitive motion or listening to vibrations. Context helps in understanding whether the motion is fast or slow, large or small. The spring mass system appears in clocks, vehicles, and bridges. It influences vibration control, energy storage, and mechanical stability. Oscillations are regular and predictable. The period depends on the mass and spring stiffness, creating repeating cycles. This system demonstrates how forces and energy interact. It teaches balance, timing, and the principles of simple harmonic motion, applicable in many natural and engineered systems. A pendulum is a weight suspended from a fixed point, so it can swing freely back and forth. Its motion is driven by gravity pulling the weight downward and the tension in the string or rod guiding its path. The fundamental idea is the transformation between potential energy at the highest points and kinetic energy at the lowest point. The essence of a pendulum is its predictable, periodic motion. A pendulum has a fixed length, a pivot point, and a mass at the end called the bob. Its motion is symmetrical around the resting position. The period of a simple pendulum depends on the length of the string and gravity, but not on the mass. It demonstrates harmonic motion, and energy continuously transfers between motion and height. The pendulum system consists of three main components: the pivot, the string, and the bob. The pivot anchors the system, the string guides the bob, and the bob provides inertia. Each component influences the motion of the others. The length of the string determines the swing time, while the weight affects the force applied to the pivot. When displaced, the pendulum accelerates toward its resting position, speeds up at the bottom, and slows down at the top. This cycle repeats in a regular pattern. Friction and air resistance gradually reduce motion, eventually stopping the pendulum unless external energy is applied. Longer strings produce slower swings, and smaller angles create nearly perfect harmonic motion. Pendulum motion can be observed in clocks, swings, or scientific experiments. Its timing and rhythm make it easy to recognize. Understanding its motion helps explain energy conservation and periodic systems in nature. Pendulums are part of mechanical systems and physics principles. They influence timekeeping, amusement rides, and scientific measurements. Their motion reflects universal laws of motion and energy transfer. Pendulums exhibit repetitive swings with constant periods. The motion is predictable, and small deviations follow harmonic rules. Observing patterns helps measure time and study forces. The pendulum teaches balance, rhythm, and energy transformation. It demonstrates how simple systems follow universal principles. Its motion provides insights into cycles in nature, engineering, and timekeeping. Mechanical waves. Mechanical waves are a way energy moves through matter. They need a medium like air, water, or a solid to travel. The main idea is that particles do not move forward with the wave. Instead, they vibrate in place and pass energy to nearby particles, like a line of students passing a clap. Mechanical waves have key traits such as wavelength, frequency, and amplitude. They can be seen as vibrations that repeat in a pattern. Sound waves travel through air, while water waves move across the surface of water. The particles stay connected and depend on each other to pass the motion along. A mechanical wave is organized into repeating parts. Crests and troughs appear in transverse waves like water waves. Compressions and rarefactions appear in longitudinal waves like sound. Each part links to the next, forming a continuous flow of motion. Mechanical waves can reflect, bend, or spread out. When a wave hits a wall, it can bounce back. When it moves into a new medium, its speed may change. These behaviors show how waves interact with their surroundings. We recognize mechanical waves through our senses. We hear sound waves with our ears and see water waves with our eyes. Understanding depends on context, such as loud or soft sounds, calm or rough water. Mechanical waves are part of larger systems like weather, music, and earthquakes. They influence communication, safety, and daily life. Waves repeat in regular cycles. This repetition helps scientists predict pitch in music or the strength of earthquakes. Mechanical waves teach that energy can travel without matter moving far. This idea helps explain many natural events and shows how connected systems work together. Wave superposition is the idea that when two or more waves meet, they combine to form a new wave. Each wave keeps its own identity, but their effects add together at every point. The main principle is simple addition of wave displacements. Waves can overlap in the same space at the same time. The combined wave depends on the size and direction of each wave. If waves move up together, the result is stronger. If one moves up and the other moves down, they can reduce or cancel each other. Each wave has parts like crest, trough, wavelength, and amplitude. During superposition, these parts line up point by point. The total displacement at any point is the sum of all individual displacements there. Superposition happens only while waves overlap. After crossing, waves continue as before. Constructive superposition makes bigger waves. Destructive superposition makes smaller waves or flat regions. These patterns can change quickly as waves move. We observe superposition in water ripples, sound beats, and light patterns. For example, dropping two stones in water creates crossing circles that rise and fall together in complex shapes. Wave superposition applies to water waves, sound waves, light waves, and even earthquake waves. It helps explain music harmony, noise cancellation, and colorful light patterns. Repeated superposition can form standing waves with fixed nodes and antinodes. These patterns are predictable and depend on wave speed and frequency. Wave superposition shows how simple rules create complex results. It teaches that interaction does not mean destruction, but combination, balance, and shared influence. Standing waves are special waves that seem to stay in one place. They form when two identical waves travel in opposite directions and overlap. Instead of moving forward, the energy is shared back and forth, creating a fixed pattern. This shows how wave interference can shape motion without overall travel. A standing wave has nodes and antinodes. Nodes are points that do not move at all, while antinodes are points that move the most. The distance between two nodes is always the same. The wave keeps its shape as long as the conditions stay unchanged. The structure of a standing wave depends on boundaries. On a string tied at both ends, the ends must be nodes. Between them, the wave arranges itself into loops. Each loop connects a node to another node, with an antinode in between. This organized pattern shows balance in motion. Standing waves do not travel across space. Instead, particles vibrate up and down in place. As time passes, the shape repeats again and again. Higher energy creates more loops, leading to different modes called harmonics. Standing waves can be seen on vibrating strings, water surfaces, or sound in air columns. Watching sand gather at nodes helps us recognize them. Careful observation makes the invisible motion clearer. Standing waves are part of a larger wave system. They explain how musical instruments produce notes. They also help in understanding light waves and microwaves. The same patterns repeat in strings, pipes, and surfaces. The spacing of nodes stays regular, leading to predictable results. Standing waves teach that motion can exist without travel. They show how balance and structure arise from simple interactions, guiding our understanding of waves across nature. Sound waves. Sound waves are vibrations that travel through a medium like air, water, or solids. When an object vibrates, it pushes nearby particles back and forth. This movement carries energy from one place to another. Sound cannot travel in empty space because there are no particles to vibrate. Sound waves have important qualities such as frequency, wavelength, and amplitude. Frequency decides how high or low a sound is. Amplitude controls how loud the sound feels. Wavelength is the distance between repeating parts of the wave. Sound exists as compressions and rarefactions, where particles crowd together and spread apart. Sound waves are organized as longitudinal waves. The particles move parallel to the direction of the wave. Each vibration links to the next particle, forming a chain of motion. The source, medium, and receiver are all connected in this system. Sound waves change speed depending on the medium. They travel fastest in solids, slower in liquids, and slowest in gases. Sound can reflect as echoes, bend around obstacles, or weaken as it spreads out. Humans recognize sound through their ears. The brain interprets vibrations as speech, music, or noise. The same sound can feel pleasant or disturbing based on situation and listener. Sound waves are part of the larger study of energy and waves. They influence communication, medicine, and technology like sonar and ultrasound. Sound waves show repeating patterns. Regular vibrations create musical notes. Predictable echoes help measure distance. Sound waves remind us that unseen motion can carry meaning. They teach how small vibrations can create powerful connections across space. The Doppler effect explains how motion changes the way waves are observed. When a sound or light source moves toward an observer, the waves seem closer together. When it moves away, the waves spread out. The key idea is that motion affects frequency and wavelength. The Doppler effect depends on relative motion between the source and the observer. It appears in sound waves, light waves, and water waves. Faster motion causes a bigger change. The observer, the source, and the medium are closely connected. The system includes a wave source, a medium, and an observer. Waves travel outward in patterns. Motion shifts these patterns. The arrangement shows compression in front and expansion behind the moving source. As speed increases, the frequency shift becomes stronger. Sound becomes higher in pitch when approaching and lower when moving away. Light shifts toward blue or red. The effect follows a clear sequence based on motion direction. The Doppler effect is noticed when a siren passes by. the pitch suddenly changes. Astronomers observe color shifts in stars to understand movement. Context helps explain what is being observed. This concept works on Earth and in space. It influences science, medicine, and technology. Radar, weather studies, and space research all rely on it. The same wave changes repeat whenever motion occurs. Approaching means higher frequency. Receding means lower frequency. These outcomes are predictable. The Doppler effect shows how motion shapes perception. It teaches that observation depends on position and movement within a system. The ideal gas law explains how gases behave by linking pressure, volume, temperature, and amount of gas. It shows that gas particles move freely, and their motion creates measurable effects we can calculate and predict. An ideal gas has particles with tiny size and no attraction between them. The particles move randomly and collide with container walls. Pressure rises with faster motion, while volume and temperature shape this behavior. The law is written as PV equals nRT. Each letter represents a physical quantity. These parts are connected so that changing one value affects the others in a clear and balanced mathematical structure. When temperature increases, particles move faster and pressure or volume increases. If volume decreases, collisions increase and pressure rises. These changes follow smooth trends that help explain gas reactions in real situations. We recognize the law through everyday examples, like balloons expanding in heat or shrinking in cold. Experiments and graphs help students see how invisible particles produce visible changes. The ideal gas law fits within chemistry and physics and supports topics like weather, engines, and respiration. It influences how scientists design systems involving air, fuel, and energy transfer. Repeated experiments show consistent relationships among variables. Predictable outcomes appear when one factor changes while others stay constant, making the law reliable for problem solving and scientific modeling. This law teaches balance and connection within systems. It reminds learners that simple rules can explain complex behavior and encourages curiosity about how unseen motion shapes the physical world. Kinetic theory of gases explains gas behavior by imagining countless tiny particles in constant motion. Each particle moves freely and collides with others and with container walls. Heat is seen as motion energy, not as a substance. Gas particles are extremely small and far apart. They move randomly in straight lines between collisions. Collisions are elastic, so total energy stays the same. Pressure appears when particles strike surfaces repeatedly. The theory connects particles, motion, and energy. Temperature links to average kinetic energy. Volume provides space for motion. Pressure results from impacts. These ideas form a simple structure that joins math with physical meaning. When temperature rises, particles move faster. Faster motion increases collision rate and force. When volume shrinks, collisions become more frequent. These changes explain gas laws through motion stories rather than formulas alone. The theory becomes clear through imagination. One can picture bouncing balls inside a box. Though particles are unseen, their effects are measured by pressure gauges and thermometers. This idea fits within thermodynamics and supports chemistry and weather science. It explains diffusion, evaporation, and air pressure. It links the tiny world of particles with large-scale observations. Regular motion leads to predictable results. Equal temperature means equal average energy. Repeated collisions create steady pressure. These patterns allow scientists to predict gas behavior. Kinetic theory of gases teaches that simple rules can explain complex systems. It shows how motion creates order. This view encourages curiosity about hidden processes shaping everyday experiences. Students learn to connect experiments, observations, and imagination while studying gases in classrooms and laboratories everywhere. First law of thermodynamics. The first law of thermodynamics explains that energy cannot be created or destroyed. It can only change from one form to another. When heat is added to a system, it either increases the internal energy or is used to do work. This idea connects heat, work, and energy into one clear rule of conservation. The law shows that energy always stays balanced. Heat entering a system raises energy, while heat leaving lowers it. Work done by the system uses energy, and work done on the system adds energy. Internal energy depends on temperature, motion of particles, and interactions between them. The law is organized around a simple relationship between heat, work, and internal energy. These elements are connected like a flow. Energy enters, transforms, and exits, but the total amount remains constant. When a gas is heated, its particles move faster. The gas may expand and push a piston, doing work. If energy leaves, particles slow down. The system responds directly to energy changes. We understand this law by observing everyday events. A hot pan cooling or an engine running both follow this rule. The law becomes clear when we track where energy goes. This law applies to engines, refrigerators, living bodies, and even Earth systems. It links physics to chemistry, biology, and engineering. Whenever heat is added, energy rises or work is done. This pattern repeats in all thermal systems and gives predictable results. The first law teaches balance and responsibility in energy use. It reminds us that energy is never lost, only transformed. A heat engine is a system that changes heat energy into useful work. It works by taking heat from a hot source, using part of that energy to do work, and releasing the remaining heat to a cold sink. The main idea is that energy moves from hot to cold, and during this movement, work can be produced. Heat engines always need three main parts: a heat source, a working substance like gas or steam, and a heat sink. They cannot convert all heat into work. Some energy is always lost as waste heat. The parts depend on each other, and if one part fails, the engine cannot function properly. The engine follows a cycle. Heat enters, work is done, and heat leaves. This cycle repeats again and again. Each step is connected, forming a closed loop that allows continuous operation. As the engine runs, the working substance expands and contracts. This movement creates motion, such as a piston moving up and down. Over time, the engine follows the same sequence, showing a steady pattern of energy flow. We recognize heat engines by observing motion or work created from heat. A car engine, a steam engine, and a power plant are clear examples. Context helps us understand their purpose, whether for transport or electricity. Heat engines are part of larger energy systems. They influence industries, transportation, and daily life by providing power and motion. All heat engines show repeated cycles and similar limits. Higher temperature difference usually means better performance. Heat engines teach us that energy has limits. They remind us to use resources wisely and understand natural laws that guide all machines. The Carnot engine is an ideal heat engine used to explain how heat can be changed into work. It shows the most efficient way an engine can work between two temperatures. The main idea is that no real engine can be more efficient than this model. It is based on the law of conservation of energy and the second law of thermodynamics. The Carnot engine works with two heat reservoirs, one hot and one cold. It uses a gas that expands and compresses in a very controlled way. Heat always flows from hot to cold. No energy is wasted in friction or heat loss. Because of this, it is perfectly efficient in theory. The engine follows a cycle made of 4 steps. 2 steps involve slow expansion and compression with heat exchange. The other 2 steps happen without heat transfer. Each step is connected smoothly, forming a closed loop called the Carnot cycle. During the cycle, heat is taken from the hot source. Some of it turns into work, and the rest is released to the cold source. The engine then returns to its starting state. This repeated cycle shows a clear pattern of energy flow. The Carnot engine is understood through diagrams and graphs. Its efficiency depends only on temperature, not on the type of gas used. This makes it easy to compare with real engines. It plays a role in physics, engineering, and climate science. It helps scientists understand limits of machines and energy use. Every Carnot engine follows the same cycle and efficiency rule. Higher temperature difference always means higher efficiency. The Carnot engine teaches that nature sets limits. It guides better engine design and encourages careful use of energy. Coulomb's law. Coulomb's law describes the force between two charged objects. It explains that the strength of the electric force depends on the size of the charges and the distance between them. If the charges are large, the force is strong. If the charges are farther apart, the force becomes weaker. This law forms the foundation of understanding electric interactions and explains why objects attract or repel each other. Electric force can be attractive or repulsive. Like charges push each other away, while opposite charges pull each other together. The force is directly proportional to the product of the charges and inversely proportional to the square of the distance. This means that even small changes in distance can greatly change the force. The force acts along the line connecting the two charges, always pointing toward or away from the other charge depending on their types. Coulomb's law organizes the relationship between charges, distance, and force. Charges are represented as points, and their interaction is calculated using a constant that ensures units are consistent. The law connects electric force with spatial positioning, showing how force vectors interact in 2 or 3 dimensions. Patterns emerge where multiple charges influence a single point, allowing predictions of net forces. Electric force changes when charges move or distance changes. Increasing charge or decreasing distance makes the force stronger. If charges move apart, the force weakens quickly. Forces can combine or cancel when multiple charges interact, creating dynamic behavior in systems like atoms or circuits. Coulomb's law can be recognized through attraction and repulsion of charged objects. Experiments with balloons, rods, or static electricity reveal how forces operate. Understanding context helps predict outcomes in real-life situations. This law influences fields such as electricity, chemistry, and engineering. It explains bonding in atoms and the behavior of electric circuits, linking microscopic and macroscopic systems. Charges show predictable patterns of attraction and repulsion. Force decreases with the square of distance, creating recurring behaviors in systems with many charges. Over time, these patterns allow accurate predictions of interactions. Coulomb's law demonstrates the fundamental nature of electric forces. It teaches that relationships between objects depend on measurable properties. This principle guides science, technology, and everyday understanding of electricity and matter. Electric potential is the energy a charged particle has due to its position in an electric field. Imagine a ball on a hill. The higher it is, the more energy it has to roll down. Similarly, a charge has energy depending on where it is in an electric field. This energy can make the charge move, creating electric current. Electric potential is measured in volts. It exists wherever there is an electric field. It can be positive or negative depending on the type of charge creating the field. Points closer to positive charges have higher potential for positive charges and lower for negative ones. Electric potential relates directly to electric potential energy, showing how energy is stored in a system of charges. Electric potential is connected to electric fields and charges. It forms a network where higher potentials push charges toward lower potentials. Equipotential surfaces are imaginary layers where the potential is the same, and no work is needed to move a charge along them. This arrangement shows how energy flows and balances in space. Electric potential changes when charges move or when fields change. Charges naturally move from high to low potential, producing current. Potential differences cause energy transfer and influence motion. If a charge is placed between 2 points with different potentials, it accelerates, similar to a ball rolling down a slope. Electric potential can be understood through voltage measurements. A voltmeter shows how strong the potential difference is between 2 points. Visualizing field lines helps understand the direction charges will move. Context matters, as potential near one charge can differ greatly from potential near many charges. Electric potential exists in circuits, atoms, and natural phenomena like lightning. It affects current, energy distribution, and stability in systems. Its influence extends to every part of electrical technology and nature. Electric potential differences always guide charges from high to low. Equipotential surfaces repeat in shape around charges. The energy transfer patterns are predictable and follow consistent rules of physics. Understanding electric potential helps explain electricity, energy storage, and power generation. It teaches the principle that energy moves from high to low, guiding the design of circuits and devices. Electric potential connects abstract energy concepts to everyday technology and natural events. An electric field is an invisible region around a charged object where it can exert a force on other charges. It represents the influence a charge has on the space around it. The essence of an electric field is the way it pushes or pulls other charges without direct contact. Electric fields exist around positive and negative charges. They point away from positive charges and toward negative charges. The strength of the field depends on the amount of charge and the distance from it. The field can interact with multiple charges at once, creating a combined effect. Electric field lines are a visual tool to show how fields are arranged. They never cross and show the direction a positive charge would move. Closed lines indicate a strong field, while distant lines indicate a weak field. Fields from different charges can combine to form new patterns. Electric fields change if the position or magnitude of charges changes. They can overlap, cancel, or strengthen each other. Moving charges can also create a magnetic effect, showing the dynamic nature of electric fields in motion. We recognize electric fields through the force they apply to charges. Using tools like test charges, we can detect direction and strength. In everyday life, static cling or sparks are small examples of electric fields at work. Electric fields influence forces at a distance, connecting particles in space. They are fundamental in circuits, lighting, and technology like capacitors. Electric field lines always originate from positive charges and end on negative ones. The patterns repeat based on charge arrangement, creating predictable behaviors. Understanding electric fields helps explain electricity and magnetism. They guide engineers and scientists in designing safe and efficient systems. Observing electric fields develops curiosity about invisible forces shaping the world. Gauss' law. Gauss' law explains how electric charges create electric fields around them. It states that the total electric flux passing through a closed surface is equal to the net charge inside divided by the permittivity of free space. Imagine a balloon around a charged object. The field lines pass through the balloon, showing the strength and direction of the field. The essence of Gauss' law is linking charge to the flow of electric field in space. Electric flux depends on the number of field lines passing through a surface. Positive charges produce outward flux, while negative charges create inward flux. The law applies to symmetric shapes like spheres, cylinders, and planes. Components are connected through the idea that the field originates from charges and spreads uniformly according to shape. Gauss' law organizes electric fields and charges into a simple structure. A closed surface, called a Gaussian surface, surrounds the charges. The arrangement helps calculate flux without knowing every field line detail. Symmetry allows simplified calculations and shows patterns of field distribution. As charge inside a surface changes, flux changes proportionally. Adding charges increases flux outward. Removing charges reduces it. Electric fields interact with multiple charges, creating combined effects that follow Gauss' law consistently. Gauss' law can be recognized when fields and surfaces are considered together. It is easier to interpret in highly symmetric cases. Understanding the concept gives a clear picture of invisible electric forces and their impact on surroundings. It connects the local electric field to the total charge inside any closed surface. It influences calculations in physics, engineering, and electronics. Its reach extends from tiny atoms to large charged objects. Flux always follows charge patterns. Outward flux for positive and inward for negative. Spherical symmetry leads to uniform flux distribution. Repetition of these rules allows predictions in multiple scenarios. Gauss' law reveals the deep connection between charge and field. It teaches that simple principles can explain complex behaviors. It is a guiding tool for solving electric field problems and understanding nature at both small and large scales. Capacitance is the ability of an object to store electric charge. It explains how electrical energy can be held and released when needed. A capacitor works like a small energy container that fills with charge when connected to a power source. Capacitance depends on three main things: the size of the plates, the distance between them, and the material placed in between. Larger plates store more charge. Smaller distance increases storage. The middle material, called dielectric, helps hold charge safely. A basic capacitor has two metal plates facing each other. They are separated by an insulating layer. Wires connect the plates to a circuit. When voltage is applied, charges move and arrange themselves on the plates. When a capacitor is connected to a battery, it charges slowly. When disconnected, it keeps the charge. If connected to a device, it releases energy. This charge and discharge process happens many times in electronic systems. Capacitance cannot be seen directly. It is understood by observing effects like stored energy or delayed current flow. In a flash camera, the bright flash shows stored charge in action. Capacitance is a small part of larger electrical systems. It helps control voltage, timing, and energy flow. It supports the working of radios, phones, and power supplies. Capacitors are used repeatedly in circuits for smoothing signals and storing energy. Their behavior follows predictable rules based on voltage and plate design. Capacitance teaches how energy can be stored and managed wisely. It shows balance between structure and function. This idea applies to many systems beyond electricity. Dielectrics are materials that do not allow electric current to flow easily. The main idea is that when an electric field is applied, charges inside the material shift slightly. This shifting does not create current, but it stores electrical energy. The essence of dielectrics lies in their ability to respond without conducting. Dielectrics have high electrical resistance. They can be solid, liquid, or gas. Inside them, positive and negative charges move a little but stay bound. This creates electric polarization. The strength of this effect depends on the material, called dielectric constant. Components inside the material work together to resist current while supporting the field. Atoms and molecules are arranged so charges are balanced. When an electric field appears, this balance slightly changes. Dipoles form and align in an organized way. Each tiny change adds up to a larger effect across the material. As the electric field increases, polarization increases. When the field is removed, most dielectrics return to normal. If the field becomes too strong, breakdown can occur and the material may conduct. Dielectrics are recognized by their use in capacitors and insulation. Their behavior is understood by observing stored charge and reduced electric force. They are part of larger electrical systems. Dielectrics affect energy storage, signal control, and safety. Most dielectrics show predictable polarization. Similar materials behave in similar ways under electric fields. Dielectrics teach how materials interact with invisible forces. They remind us that even without motion, change and energy can exist quietly within systems. Current density explains how electric current spreads through a material. It tells us how much electric charge flows through a specific area in a given time. Instead of only asking how much current flows, this idea asks where and how tightly the current flows. The main principle is simple. Same current can behave differently depending on area. Current density depends on current and cross-sectional area. It increases when the area becomes smaller and decreases when the area becomes larger. It has both size and direction, so it is a vector quantity. The direction matches the direction of positive charge flow. Imagine a wire as a road and charges as moving vehicles. The wire area is the road width. Current density shows how crowded the road is. All small areas inside the wire together form the full path for charge movement. Each tiny area carries its own share of current. When voltage increases, charges move faster and current density rises. When the wire heats up, resistance increases and current density may change. In narrow regions, current density becomes high and heating increases. Current density is understood by comparing different wires carrying the same current. A thin wire feels hotter than a thick one. This helps us sense current density effects. Current density links electricity with material properties. It affects heating, safety, and energy transfer in circuits. Higher current density often leads to more heat. Uniform wires show uniform current density. Sharp edges show higher values. Current density teaches that distribution matters, not just quantity. It guides safe design of wires and devices across electrical systems. Kirchhoff's laws. Kirchhoff's laws explain how electric current and voltage behave in a circuit. The main idea is that electric charge and energy are conserved. What flows into a point must flow out, and energy supplied must equal energy used. There are two laws. The current law deals with current at a junction. The voltage law deals with voltage in a loop. These laws apply to simple and complex circuits. They connect batteries, wires, and resistors into one working system. A circuit is arranged using nodes, branches, and loops. Nodes are meeting points of wires. Branches carry current. Loops form closed paths. Kirchhoff's laws organize these parts so relationships between current and voltage can be calculated clearly. When a battery is added, current starts to flow. If resistance changes, current also changes. Kirchhoff's laws help track these changes step by step. They show how current splits and how voltage rises and falls around a loop. These laws can be understood by careful observation and calculation. Drawing circuit diagrams makes the idea clearer. Each junction and loop tells a story of balance and flow. Kirchhoff's laws work inside larger electrical systems like homes and devices. They influence how engineers design safe and efficient circuits. The same balance appears again and again. Current entering equals current leaving. Voltage gains equal voltage drops. This predictability helps solve problems. Kirchhoff's laws teach balance and conservation. They show that systems follow rules. Understanding them builds strong thinking skills useful beyond physics. A magnetic field is an invisible region around a magnet or a current-carrying wire where magnetic force can be felt. It is created due to moving electric charges and is a basic part of magnetism. The main idea is that magnets and electric currents influence space around them and can attract or repel certain materials. Magnetic fields have direction and strength. They are strongest near the poles of a magnet. Field lines show how the field exists in space. These lines move from the North Pole to the South Pole outside the magnet. Magnetic fields affect iron, steel, and electric charges in motion. The magnetic field is arranged in smooth curved lines called magnetic field lines. These lines never cross each other. Closer lines mean a stronger field. Around a straight current carrying wire, the field forms circular patterns. In bar magnets, the field is spread symmetrically. Magnetic fields change when the current changes or when magnets move. Increasing current increases field strength. When two magnetic fields meet, they can combine or weaken each other. This behavior explains electric motors and generators. Though invisible, magnetic fields can be seen using iron filings or a compass. A compass needle aligns with the field and shows direction. This helps us understand Earth's magnetic field. Magnetic fields are part of a larger electromagnetic system. They affect electricity, communication devices, and navigation systems. Earth's field protects life from harmful space radiation. Magnetic fields always form closed loops. Similar pole interactions repeat attraction and repulsion patterns. These behaviors are predictable. Magnetic fields show how unseen forces shape the physical world. They teach that invisible systems can have powerful effects in daily life. The Lorentz force explains how electric and magnetic fields act on a moving charged particle. It tells the story of how invisible fields create visible motion. When a charge moves through space where fields exist, it feels a force that changes its path or speed. This force depends on three things: electric charge, velocity, and field strength. The electric part can push or pull a charge. The magnetic part only acts when the charge is moving. The direction of motion, field direction, and force are all linked. The Lorentz force is formed by combining electric force and magnetic force. These parts work together as one system. The electric field affects motion directly. The magnetic field bends motion sideways. Both follow clear mathematical rules. As the charge moves, the force may change its direction or energy. A particle can move in a straight line, curve, or circle. Faster motion and stronger fields lead to stronger effects. We cannot see the force, but we observe its results. Curved paths in particle tracks and moving charges in wires help us understand it. Context matters, such as whether fields are present or not. The Lorentz force is part of electromagnetism. It affects circuits, motors, and space particles. It links small particle behavior to large systems. Charges often follow circular or spiral paths. Predictable motion appears in repeated conditions. The same rules apply in labs and nature. The Lorentz force shows how hidden forces shape motion. It teaches that movement and environment are deeply connected. Understanding it helps explain modern technology and the universe. The Biot-Savart law explains how electric current creates magnetic fields. It tells a story where moving charges shape invisible circles of influence in space. The core idea says that a small piece of current produces a small magnetic effect, and all pieces together build the total field. Closer points feel stronger effects, while farther points feel weaker ones. The field curves around the wire, forming circular paths that follow the right-hand rule. Each tiny segment of a current-carrying wire acts like a source. These segments combine through addition to form a complete pattern. The law connects geometry, current flow, and distance into one organized mathematical picture. When current increases, the magnetic field grows stronger. When the path bends, the field shape bends too. In loops and coils, many segments reinforce one another, creating concentrated regions of magnetic influence. The magnetic field cannot be seen directly, but iron filings and compasses reveal the pattern. This law works at the level of steady currents and simple conductors. It supports larger ideas like electromagnets, motors, and generators used in daily technology. Circular symmetry appears again and again around straight wires. Repeated arrangements of loops create predictable fields, helping engineers design controlled magnetic systems. The Biot-Savart law teaches that small actions can combine into powerful results. Ampere law. Ampere law is a fundamental principle in physics that explains the relationship between electric currents and magnetic fields. It states that a current flowing through a conductor produces a magnetic field around it. The essence of Ampere law lies in connecting electricity with magnetism, showing that moving charges generate circular magnetic fields. It forms one of the key foundations of electromagnetism. The magnetic field created by a current-carrying conductor is directly proportional to the current. It follows a circular pattern around the conductor, and its direction can be predicted using the right-hand rule. Multiple currents can interact, and their magnetic fields combine vectorially. The field strength diminishes as the distance from the conductor increases, showing a clear inverse relationship. Ampere law is mathematically expressed as the integral of the magnetic field around a closed loop equals the permeability times the enclosed current. This creates a framework to calculate magnetic effects from any current configuration. The law interconnects conductors, magnetic fields, and surrounding space in a structured, predictable manner. Magnetic fields change when the current changes. Increasing current strengthens the field, while reversing current reverses the field direction. When multiple conductors carry current, their fields interact, sometimes strengthening or canceling each other. This dynamic behavior allows design of electromagnets and electrical devices. Ampere law can be observed by placing a compass near a current-carrying wire. The compass needle aligns tangentially to the magnetic field lines. Understanding the law helps visualize invisible magnetic effects created by electricity. It influences electromagnet design, electric motors, and generators. It is a central part of Maxwell's equations, linking electricity, magnetism, and the broader electromagnetic system. Magnetic fields always form closed loops. The strength and direction follow consistent rules, producing predictable patterns around conductors. Ampere law reveals the deep connection between electricity and magnetism. It guides engineers and scientists to manipulate currents and fields, shaping modern technology and deepening understanding of natural forces. Electromagnetic induction occurs when a changing magnetic field creates an electric current in a conductor. The essence of this phenomenon is that moving magnetic lines of force near a wire push electrons, producing electricity. Michael Faraday discovered this principle, showing that electricity and magnetism are deeply connected. It is essential that the magnetic field changes, or the conductor moves relative to the field. The induced current depends on the strength of the magnetic field, the speed of change, and the number of turns in the wire. This relationship shows that magnetism can directly produce electricity without physical contact. A typical setup includes a magnet, a coil of wire, and often a galvanometer to detect current. When the magnet moves toward or away from the coil, the magnetic flux through the coil changes. The coil and magnet interact to produce a measurable flow of electrons in the wire. The induced current increases with faster motion or stronger magnetic fields. Reversing the motion reverses the current direction. This dynamic allows electric generators to convert mechanical motion into electrical energy continuously. Electromagnetic induction can be recognized through a galvanometer or light bulb connected to a coil. Observing the bulb light up when a magnet moves near the coil demonstrates the invisible transfer of energy from magnetism to electricity. It is fundamental to electric generators, transformers, and wireless charging. Its influence extends to all modern electrical systems, shaping how energy is produced, transmitted, and used in daily life. The induced current follows predictable patterns based on Faraday's law. A continuous motion of the magnet produces alternating current, while constant movement in one direction produces direct current. Electromagnetic induction reveals that motion and magnetism can create electricity, showing the unity of natural forces. It teaches that observation and understanding of simple interactions can lead to inventions that power the world. Faraday's law describes how a changing magnetic field can create an electric current in a conductor. The fundamental idea is that electricity and magnetism are closely linked. When the magnetic field around a wire changes, it pushes electrons, producing a current. This principle is the foundation of electric generators and transformers. Faraday's law depends on the speed of the magnetic field change, the number of wire loops, and the area of the loop. A faster change produces a stronger current. The law shows that electricity can be induced without direct contact, relying only on magnetic influence. The current's direction depends on the way the magnetic field changes. The law is expressed mathematically as the induced voltage equals the negative rate of change of magnetic flux. Magnetic flux combines the field strength and the area it passes through. The elements of field, conductor, and motion are interconnected. Each affects the amount and direction of induced current. When a magnet moves toward a coil, the current rises. If the magnet moves away, the current reverses. Rapid motion increases current strength. The system adapts to changes in field and motion continuously. Faraday's law can be observed with simple experiments. Moving a magnet through a coil of wire lights up a bulb. In daily life, it explains how electricity reaches homes from power plants. Context helps understand whether motion or magnetic change causes induction. The law connects mechanics, electricity, and magnetism. It influences generators, motors, and transformers. It shows energy conversion from motion to electricity and links magnetic and electric systems. Current appears whenever the magnetic field changes. Faster changes create stronger currents. Repeated motion leads to repeated induction, showing a clear pattern of cause and effect. Faraday's law demonstrates the unity of physical forces. It teaches that motion and magnetism create electricity, guiding modern technology and energy systems. The principle reminds us that simple physical changes can have powerful effects. Lenz's law is a principle in physics that explains how electric currents respond to changing magnetic fields. The fundamental idea is that any induced current will flow in a direction that opposes the change that produced it. Imagine moving a magnet toward a coil. The coil generates a current that pushes back against the approaching magnet. This principle reflects nature's way of resisting sudden changes in energy. Lenz's law always produces currents that act to oppose change. The induced current is proportional to the rate of change of the magnetic field. It exists in metals and conductive loops whenever magnetic flux changes. The relationship between the magnetic field, induced current, and motion is consistent and predictable. If the magnetic flux increases, the induced current creates a field to reduce it, and if it decreases, the current boosts it. The structure involves a magnetic field, a conductor, and relative motion. Magnetic lines of force intersect the conductor, creating electric potential. The interaction forms a loop of cause and effect, where motion changes the field, and the field generates current, which then influences the motion. This cycle repeats wherever magnetic flux varies. Lenz's law responds immediately to changes in magnetic flux. Faster changes produce stronger currents. If the magnet moves away, the current reverses to maintain the previous magnetic state. In circuits, the law can cause energy to be stored as heat or mechanical resistance, showing its dynamic influence. We recognize Lenz's law through experiments like moving magnets near coils or dropping magnets in copper tubes. The motion slows, and a current is detected, demonstrating the law. Understanding comes from observing opposition in action. It applies to electrical generators, transformers, and motors. Its influence extends to energy conservation, electromagnetic braking, and induction processes across electrical systems. The recurring pattern is opposition to change. Every time magnetic flux varies, induced currents appear in a consistent direction, making outcomes predictable in design and experiment. Lenz's law shows nature's balance. It guides engineers to harness electricity efficiently, prevents sudden energy spikes, and teaches the principle of action and reaction in energy systems. Inductance is the property of a conductor or coil that resists changes in electric current. It stores energy in a magnetic field when current flows through it. The essence of inductance lies in the relationship between electricity and magnetism, showing how moving charges create magnetic effects that influence the circuit itself. Inductance depends on the number of coil turns, the coil area, and the material of the core. It manifests as opposition to sudden changes in current, measured in henries. Components like wires and coils work together to produce self-inductance, while coupled coils produce mutual inductance between circuits. A simple inductor consists of a wire wound into a coil. The arrangement of turns and the type of core affect its strength. Elements such as resistance and capacitance often connect with inductance in circuits, creating patterns like oscillations in LC circuits. When current increases, the inductor generates a magnetic field that resists the change. When current decreases, the collapsing field induces a current in the same direction as the original. These interactions create predictable trends like energy storage and release cycles. Inductance is observed in transformers, motors, and electronic filters. By measuring voltage and current changes over time, one can understand how strongly an inductor opposes current variation. Inductance affects energy flow, timing in circuits, and electromagnetic behavior in larger systems. It links electricity with magnetic phenomena, influencing other components like resistors and capacitors. Inductors produce repeating oscillations in AC circuits. Their behavior follows consistent mathematical laws and predictable energy transfer patterns. Inductance teaches the connection between motion and energy storage. It shows how natural forces shape technological design and guides engineers in controlling current and voltage effectively. Maxwell's equations describe how electric and magnetic fields behave and interact. They show that electricity and magnetism are parts of one unified force called electromagnetism. The fundamental idea is that electric charges create electric fields, moving charges produce magnetic fields, and changing fields influence each other. Electric fields radiate outward from charges, while magnetic fields form loops around currents. These fields can exist in space without material substance. They influence each other through specific relationships. A changing electric field creates a magnetic field, and a changing magnetic field generates an electric field. This interplay forms the basis of light and electromagnetic waves. The four Maxwell equations are Gauss's law for electricity, Gauss's law for magnetism, Faraday's law of induction, and Ampere-Maxwell law. Together, they form a structured system linking charges, currents, and fields. Each law addresses a distinct aspect but fits into the overall framework to describe electromagnetic behavior. Maxwell's equations explain how fields evolve over time. A moving charge creates a changing magnetic field. A changing magnetic field induces an electric field. This sequence allows energy to move through space as waves, including visible light, radio waves, and X-rays. We can recognize these fields through their effects. A compass needle reacts to a magnetic field. Static electricity shows the presence of electric charges. Experiments with coils and magnets reveal the patterns of induced currents and fields. These equations apply everywhere, from atoms to galaxies. They guide the design of electric circuits, motors, antennas, and communication systems. Their influence extends to modern technology and natural phenomena like lightning and auroras. Electromagnetic waves repeat at regular frequencies. The alternating rise and fall of fields create predictable patterns that can be harnessed for radio, light, and energy transmission. Maxwell's equations unify electricity, magnetism, and light. They demonstrate that natural forces are interconnected. Understanding them teaches us the principles of energy transfer, wave propagation, and the hidden order in physical systems. Electromagnetic waves are invisible energy waves that travel through space carrying light, heat, and information. At their essence, they are created when electric and magnetic fields interact and move together. These waves do not need a material to travel through and can move across empty space. Electromagnetic waves have wavelength, frequency, and speed. Wavelength is the distance between two peaks of the wave. Frequency is how many waves pass a point in 1 second, and the speed is how fast the wave travels. The electric and magnetic parts are always perpendicular to each other and to the direction of travel. They can reflect, refract, and bend around objects, showing their flexibility and influence. Electromagnetic waves are arranged in a spectrum from radio waves with long wavelengths to gamma rays with very short wavelengths. Each type interacts differently with matter. The spectrum shows a continuous pattern where each wave type connects with the next, forming a complete energy system. Electromagnetic waves spread outward, lose intensity with distance, and can change direction when entering new materials. They can combine or cancel each other, producing patterns like light interference. Waves carry energy that can heat objects, power devices, or transmit signals across the world. We recognize some waves through sight as visible light, feel them as warmth from the sun, or detect them as signals in radios and phones. Awareness depends on the wave type and the tools we use to sense it. These waves influence communication, medicine, astronomy, and daily life. They connect energy and information across systems, shaping technology and nature together. Waves show repeating crests and troughs, predictable frequencies, and rhythmic behaviors that help scientists design antennas, lasers, and other devices. Electromagnetic waves are a bridge between electricity, magnetism, and energy. They teach us that invisible forces can shape visible life, showing the unity of natural systems and the power of understanding energy in motion. AC circuits involve the flow of electric current that changes direction periodically. Unlike direct current, which moves steadily in one direction, alternating current rises and falls in a smooth wave. The underlying principle is the use of voltage that alternates sinusoidally, allowing energy to be transferred efficiently over long distances. AC circuits have voltage and current that continuously vary over time. They are characterized by amplitude, frequency, and phase. Components such as resistors, capacitors, and inductors react differently to AC, creating relationships that determine overall circuit behavior. An AC circuit is organized with a power source, conductors, and load elements. Resistors limit current, capacitors store energy, and inductors oppose changes in current. These elements are interconnected in series, parallel, or combinations, forming a complete path for alternating current. AC circuits change constantly as voltage and current oscillate. Phase differences appear between current and voltage in reactive components. Over time, the circuit responds to frequency changes, showing patterns of resonance or energy storage. AC behavior is recognized by oscilloscopes as waveforms. The shape, height, and spacing of waves reveal amplitude, frequency, and phase. Context such as household electricity or radio signals helps in interpreting circuit activity. AC circuits influence electrical grids, communication systems, and appliances. Their principles integrate with transformers and motors, impacting the efficiency and stability of larger systems. Voltage and current repeat periodically, forming predictable sinusoidal patterns. Peaks, zero crossings, and cycles occur regularly, allowing engineers to design timing and synchronization. AC circuits demonstrate how energy can move efficiently and safely. Understanding them teaches control, measurement, and adaptation in electrical systems, guiding modern technology in homes and industries. The Poynting vector represents the flow of energy in an electromagnetic field. It shows the direction in which energy moves and how fast it travels. Imagine sunlight streaming through a window. The energy carried by light travels in a certain direction. The Poynting vector points along that direction, connecting electric and magnetic fields into a moving energy stream. The Poynting vector is a vector quantity. Its magnitude tells the rate of energy transfer per unit area. Its direction is perpendicular to both the electric and magnetic fields that create it. If the fields are strong, the Poynting vector is large, meaning more energy flows. If the fields are weak, the vector is smaller. It depends on the cross product of the electric field and magnetic field, forming a right-angle relationship between components. Energy in electromagnetic waves moves through space following the Poynting vector. The vector links the electric field and magnetic field in a precise geometric structure. Together, they form a continuous pattern where energy flows smoothly along the vector. Each part of the field influences the other, maintaining a balanced, interdependent system. The Poynting vector changes with the intensity and direction of the fields. When waves reflect, bend, or pass through different materials, the vector adjusts. Energy flows along curved or straight paths, showing how the system adapts. Over time, these changes create predictable energy transfer patterns. You can visualize the Poynting vector as tiny arrows pointing along the direction energy travels. By understanding the fields, one can anticipate how energy moves. Context, like space or medium, affects how strong or fast the energy flows. The vector is part of the larger electromagnetic system. It influences circuits, antennas, and even light traveling through space. Its behavior helps explain energy transfer in many physical processes. Energy flows in waves, and the Poynting vector repeats in alignment with wave patterns. These regularities predict how energy distributes in space over time. The Poynting vector shows that energy is directional and dynamic. It helps us design electrical systems, understand radiation, and harness energy efficiently. It teaches that understanding movement and connection reveals deeper insights into natural processes. The photoelectric effect occurs when light shines on a metal surface and causes it to release electrons. This happens because light carries energy in packets called photons. When a photon hits an electron, it transfers its energy, and if the energy is strong enough, the electron escapes from the metal. This idea shows that light behaves not only as a wave, but also as a particle. The main characteristics of the photoelectric effect include the need for a minimum light frequency, called the threshold frequency, for electrons to be emitted. The number of emitted electrons increases with light intensity, but the energy of each electron depends on the light frequency, not intensity. Electrons are released instantly when the correct frequency shines on the surface. The system includes light as the energy source, metal as the electron provider, and emitted electrons as the output. The interaction follows a clear sequence. Photon strikes metal, electron absorbs energy, and electron escapes. Components are linked through energy transfer from light to matter. Electrons are emitted immediately if the light frequency is sufficient. Increasing light intensity raises the number of electrons, but does not increase their energy. Changing light frequency changes electron energy, but not quantity, if intensity is constant. We recognize the photoelectric effect by observing electric current created when light hits metal. The effect shows the connection between light energy and matter. Its outcome depends on the type of metal and light frequency. This phenomenon is part of quantum physics. It influences electronics, solar cells, and photodetectors, showing the link between light and electricity in practical systems. The effect repeats whenever light of sufficient frequency hits metals. Threshold frequency and intensity patterns are predictable and consistent across experiments. The photoelectric effect helped develop quantum theory. It shows energy comes in discrete packets and guides the design of devices that convert light into electricity, revealing the deep relationship between energy, light, and matter. Wave-particle duality is the idea that light and matter can behave both as particles and as waves. This principle shows that tiny objects, like electrons or photons, do not fit neatly into one category. At its essence, it reveals the hidden complexity of nature and challenges our everyday intuition about how things exist. Particles have mass, occupy space, and can collide with other particles. Waves spread out, interfere, and create patterns. Light and electrons can show interference like waves, but also hit a screen at single points like particles. These dual traits exist together, appearing differently depending on how they are observed. The components are related through energy and momentum, linking their wave and particle aspects. The structure of wave-particle duality involves the quantum world, where particles have probabilities of being in different places. Waves describe these probabilities, while particle properties describe interactions. Elements are interconnected through quantum laws, and patterns emerge when observations are repeated, revealing the underlying structure of matter and energy. Wave-particle duality evolves with observation. Without measurement, an electron acts like a wave. When measured, it behaves like a particle. Interactions with other particles or barriers change the outcomes, creating sequences of interference or scattering patterns. The dynamics show that reality depends on both the system and the observer. We recognize wave-particle duality through experiments like the double slit. Context changes our interpretation, as the same object can appear as a particle in one setup and a wave in another. Awareness grows when we see these effects repeatedly. Duality exists at the quantum level, but affects technologies like lasers, electron microscopes, and semiconductors. Its influence spreads into physics, chemistry, and electronics. Regular interference patterns and particle impacts show predictability. Recurring results in experiments confirm the dual nature across different systems. Wave-particle duality teaches that nature cannot always be divided into simple categories. It guides scientific thinking, inspiring curiosity and deeper exploration of the universe at its smallest scales. De Broglie wavelength is the idea that all matter, not just light, behaves like a wave. It suggests that particles such as electrons have a wavelength associated with their motion. The essence is that moving objects can show both particle and wave characteristics, linking matter to energy in a surprising way. The wavelength depends on the particle's momentum. Faster particles have shorter wavelengths, and slower particles have longer wavelengths. It manifests as diffraction or interference when particles pass through narrow openings or slits. Momentum and wavelength are inversely related, forming a clear connection between motion and wave behavior. The concept connects particle mass, velocity, and Planck's constant in a single formula. Each particle carries a hidden wave aspect, and all components fit into a predictable mathematical structure. This framework explains why microscopic particles show wave patterns, while larger objects do not. As particle speed increases, its wavelength decreases. Patterns emerge in interference experiments, showing sequences of bright and dark bands. Particles interact with barriers and openings in ways similar to light waves, revealing their dual nature in a dynamic system. De Broglie waves can be observed in experiments like electron diffraction. Understanding comes from linking motion to wave effects. In different contexts, the wavelength can be very small or measurable, changing how we see the particle. It applies mainly to microscopic particles, influencing atomic and subatomic processes. It shapes how electrons move in atoms, and how modern devices like electron microscopes work. Interference and diffraction patterns repeat predictably. This regularity allows scientists to measure wavelengths and confirm wave-particle duality. The concept bridges classical and quantum physics. It teaches that matter has hidden dimensions and shows the unity of energy and motion in nature. The uncertainty principle is a fundamental idea in quantum physics. It explains that certain pairs of properties of particles, like position and momentum, cannot be measured exactly at the same time. The more precisely one property is known, the less precisely the other can be determined. This principle reveals the limits of observation at very small scales. It shows that nature is inherently uncertain at the quantum level. This uncertainty is not due to experimental errors, but is a real property of particles. The principle manifests in all microscopic systems and connects properties like energy, time, position, and momentum. These properties influence each other in ways that cannot be separated completely. The principle fits into the structure of quantum mechanics. Particles are represented as wave functions, which describe probabilities rather than exact values. Position and momentum are interconnected, forming a framework where observation affects the system. Patterns of probability govern how particles behave. Particles do not have fixed trajectories. Their behavior evolves as probabilities shift. Observing a particle affects its state, and sequences of measurements show trends rather than exact predictions. Interactions are dynamic and uncertain, creating unique patterns. It can be understood through experiments like the double-slit experiment. Awareness comes from recognizing limits to measurement and interpretation. Context matters because the principle becomes more visible at atomic and subatomic scales. It influences all quantum systems and affects chemistry, electronics, and even astrophysics. The uncertainty principle sets boundaries for what can be known and predicts effects on other processes. Uncertainty repeats across similar systems. Certain regularities, like energy fluctuations, appear predictably within the limits set by the principle. The principle teaches that the universe has intrinsic limits. It encourages curiosity, careful observation, and understanding that some aspects of reality are probabilistic and interconnected. The Schrödinger equation is the heart of quantum mechanics. It describes how the state of a particle or system changes over time. At its core, it tells us the probabilities of where a particle might be or how it behaves instead of exact positions. Imagine a tiny particle moving like a wave through space. This equation captures that wave-like motion mathematically. It has a wave function called psi that contains all information about a system. The equation is linear, meaning solutions can be added together. Energy and momentum are closely connected to the wave function. The Schrödinger equation connects the particle's behavior in space and time and predicts outcomes that can be observed in experiments. The equation has two main forms, time-dependent and time-independent. The time-dependent version shows how systems evolve, while the time-independent form focuses on fixed energies. Components like kinetic energy, potential energy, and the wave function interact through mathematical operations, revealing patterns in particle behavior. Solutions of the equation show oscillating wave patterns that can interfere or spread. Over time, particles may shift between states, and probabilities can change. Bound systems like electrons and atoms create standing waves that remain stable, forming energy levels. The Schrödinger equation is recognized through experiments like the double-slit experiment. Observing interference patterns gives evidence of the wave function. Its meaning depends on the context of particles or fields being studied. It applies to atoms, molecules, and larger systems in physics and chemistry. Its predictions influence technologies such as semiconductors and lasers, linking microscopic rules to real-world processes. Energy levels, resonance, and wave interference are recurring outcomes. Probability distributions often repeat under similar conditions, showing order within quantum uncertainty. This equation reveals that the universe at small scales is not deterministic but probabilistic. It teaches that understanding systems deeply requires observing patterns and embracing uncertainty while still making predictions. The particle in a box is a simple model in physics and chemistry that helps us understand how tiny particles, like electrons, behave when they are confined in a small space. Imagine a particle trapped inside a tiny room with walls it cannot cross. The particle cannot escape, so it can only move within the boundaries. The essence of this model is that the particle's energy is limited to certain fixed values, called quantized energy levels. A particle in a box has specific traits. It cannot exist outside the box. Its energy cannot take just any value but jumps in steps. The particle's position is uncertain, but its motion follows predictable patterns. The size of the box determines the spacing of these energy levels. Smaller boxes lead to higher energy levels, while larger boxes allow lower energy levels. The system has a simple structure. The particle moves along a single dimension, 2 dimensions, or 3 dimensions depending on the model. Each dimension adds complexity, creating multiple energy levels. The particle's wave function describes its probability of being at different positions inside the box. Energy levels and wave functions are interconnected mathematically. The particle vibrates or moves inside the box without leaving it. Its energy can change only by jumping between allowed levels. This creates patterns in motion and energy absorption. Interactions with external forces or light can cause transitions between levels. This concept can be observed through experiments like spectroscopy, where energy jumps are detected as light absorption or emission. It helps explain how tiny particles behave in confined spaces. The particle in a box model influences chemistry, physics, and nanotechnology. It explains electron behavior in atoms, molecules, and quantum dots. Energy levels are evenly spaced in simple cases. Higher levels repeat similar wave shapes with more nodes. This predictability forms the basis for understanding quantum behavior. The model shows that nature at small scales is discrete, not continuous. It teaches that confinement changes energy and motion, guiding principles in chemistry, electronics, and material science. Quantum tunneling. Quantum tunneling is a phenomenon in physics where particles pass through barriers that they normally could not overcome. At its essence, it shows that tiny particles do not always follow the strict rules of classical physics. Instead, they behave like waves, allowing them to appear on the other side of obstacles without the energy to climb over. This challenges our everyday ideas of how objects move and interact. Tunneling occurs at the microscopic scale, mostly with electrons, protons, and atoms. It is probabilistic, meaning there is a chance a particle can tunnel but not a guarantee. The phenomenon depends on the particle's energy, the width of the barrier, and the barrier's height. Components interact through wave-like behavior, creating patterns of high and low probabilities for tunneling. Quantum tunneling is described through quantum mechanics. Wave functions represent the particle's possible locations and energies. Barriers are modeled as potential energy walls, and the particle's interaction with them follows mathematical rules. These elements connect to predict the likelihood of tunneling and the particle's path. Particles may tunnel instantly or over time depending on conditions. Sequences of tunneling events can lead to observable effects like radioactive decay. Within systems, tunneling enables reactions or movements that classical physics cannot explain. We recognize tunneling indirectly through experiments, such as scanning tunneling microscopes. Its interpretation changes with context, appearing unusual at the human scale but normal in quantum systems. Tunneling influences chemistry, electronics, and nuclear physics. It enables technologies like semiconductors and nuclear fusion in stars. It often occurs in repeated scenarios like electron transport in circuits. Probabilities follow predictable mathematical distributions. Quantum tunneling shows nature's hidden possibilities. It teaches that limits are not always absolute and that the universe operates with surprising flexibility and mystery. The quantum harmonic oscillator is a model that shows how tiny particles, like electrons or atoms, move in a regular, back-and-forth motion when trapped in a force field. Its essence lies in combining the idea of classical oscillation with quantum rules. Unlike a swinging pendulum, it cannot have just any energy. Energy comes in fixed steps called quantized levels. It has equally spaced energy levels. Each level has a wave function that shows where the particle is likely to be. The particle cannot sit still at zero energy. Its position and momentum are linked by the uncertainty principle. The oscillator can be in a mixture of states, showing probabilities rather than certainties. The system is structured around a potential well shaped like a bowl. The lowest energy state sits at the bottom, while higher states rise above. Ladder operators connect these states, letting particles move up or down in energy. The energy levels, wave functions, and operators form an interconnected framework. Particles oscillate with fixed energy jumps. They may absorb or release energy in the form of photons. The motion repeats in patterns, and transitions follow strict quantum rules. We recognize it through spectral lines, vibrations in molecules, or measurements in labs. Observations show probabilities of location, not exact positions. Context changes how we interpret the energy or motion. It models vibrations in molecules, atoms in solids, and even light modes in cavities. It influences other processes like chemical reactions and heat capacity. Energy levels are evenly spaced. Wave functions repeat in shape with higher states. Oscillations follow predictable frequencies. This concept teaches how the quantum world differs from classical intuition. It shows the importance of energy quantization and probabilistic behavior. It guides understanding of many physical and chemical phenomena. Quantum angular momentum is a way to describe the rotation of tiny particles like electrons and atoms. Unlike a spinning top we see in everyday life, this rotation follows special rules that come from quantum physics. It tells us how particles move and interact in atoms and molecules, forming the foundation of many physical phenomena. At its essence, quantum angular momentum is about how motion and rotation exist in discrete amounts instead of being continuous. Quantum angular momentum has fixed sizes and directions. It exists in steps or levels called quanta. Components include orbital angular momentum, coming from a particle moving around a point, and spin angular momentum, an intrinsic property of particles. These components combine in specific ways, following clear rules, and cannot take arbitrary values. The structure of quantum angular momentum is arranged using numbers called quantum numbers. These numbers define magnitude, direction, and how different angular momenta combine. Particles interact through these rules, producing patterns that are predictable and mathematically organized. Angular momentum changes through interactions, like collisions or energy absorption. It follows sequences and selection rules, meaning transitions happen in specific steps. The system evolves according to probabilities rather than certainty. Quantum angular momentum can be observed indirectly through atomic spectra or magnetic effects. Its behavior can be interpreted relative to the particle's environment, like how electrons align in a magnetic field. It is a key part of quantum mechanics, influencing chemical reactions, magnetism, and atomic structure. It shapes the properties of matter on a very small scale, but has consequences in larger systems. Angular momentum shows regularities, such as quantized energy levels and allowed transitions. These patterns help predict outcomes in experiments and technologies like lasers. Understanding quantum angular momentum reveals the hidden order in nature. It teaches that even in the smallest scales, rules govern motion and interactions, guiding advancements in science and technology. Spin is a fundamental property of tiny particles like electrons, protons, and neutrons. It is a type of intrinsic angular momentum. Unlike a spinning top, particle spin does not involve physical rotation, yet it behaves as if the particle is turning around an invisible axis. Spin has specific values such as 1/2 or 1. It can point in different directions, often called up or down. Spin affects magnetic properties, energy levels, and interactions with other particles. Particles with the same spin follow certain rules, while those with opposite spins can pair together. Spin is organized in a system through quantum mechanics. Particles align in magnetic fields and influence energy arrangements. Collections of particles with aligned spins form patterns that can create magnetism in materials. Spin can change direction under external influence, such as magnetic fields. It can precess, flip, or combine with other spins to form new states. This dynamic behavior explains phenomena like electron pairing and superconductivity. Spin cannot be seen directly but is detected through its effects. Experiments like the Stern-Gerlach experiment reveal spin directions. Understanding spin helps explain chemical bonding and magnetic properties. Spin is essential in atomic and subatomic systems. It influences the structure of atoms, molecules, and materials. Spin also plays a role in technology like MRI machines and quantum computing. Spin follows predictable patterns based on quantum rules. Pauli's exclusion principle ensures no two identical particles share the same state. Spins align or oppose to create stable configurations. Spin reveals the hidden order of the microscopic world. It teaches how tiny properties govern large-scale behavior. Recognizing spin allows deeper insight into nature and advances science and technology. Hydrogen atom. The hydrogen atom is the simplest type of atom. It is made up of a single proton at its center, called the nucleus, and one electron that moves around it. This atom is the building block of all matter and represents the basic idea of how elements form. Its essence lies in the balance between the positive charge of the proton and the negative charge of the electron, which keeps the atom stable. Hydrogen is colorless, odorless, and highly flammable. The electron exists in specific energy levels around the nucleus, which determines how the atom behaves in chemical reactions. The proton defines its identity as hydrogen, while the electron allows it to bond with other atoms. The simplicity of hydrogen makes it a key element in understanding atomic structures. The hydrogen atom is arranged with the proton at the center and the electron in a surrounding cloud. The electron does not move in a fixed path, but occupies regions where it is most likely to be found. This arrangement shows how energy and charge interact to maintain stability. Patterns of interaction emerge when hydrogen forms molecules like H2. The electron can gain or lose energy, jumping between levels and producing light. Hydrogen reacts easily with oxygen to form water. Its behavior changes under different temperatures and pressures, showing dynamic interactions with the environment. Hydrogen can be detected in stars and water. Understanding its electron and proton structure helps explain chemistry and physics. Its simplicity makes it a reference point for learning about other atoms. Hydrogen is part of the universe and essential for life. It fuels stars, forms water, and is used in fuels and energy systems. Its presence influences chemical reactions and energy flow. Hydrogen atoms combine in predictable ways to form molecules. Light emission from electrons produces spectral lines, which repeat for each energy transition. The hydrogen atom teaches the basic principles of matter. Its study guides chemistry, physics, and energy science. Understanding hydrogen inspires curiosity about the universe and the building blocks of life. Perturbation theory is a method used to find approximate solutions to problems that cannot be solved exactly. It works by starting with a simple system we understand and then adding a small change or disturbance. This small change is called a perturbation, and it helps us understand how the system behaves when it is slightly altered. Think of it like nudging a calm pond and watching how the ripples spread. Perturbation theory depends on the disturbance being small. The results gradually adjust as the perturbation changes. It separates the problem into an easy part and a complex part. Components are connected because the solution of the simple system guides the behavior of the full system. The framework begins with the known solution of the simple system. Next, the perturbation is introduced in steps or orders. Each step refines the approximation. The first step gives a rough estimate, and later steps improve accuracy. The system changes gradually with each added perturbation. Corrections accumulate and show trends toward the final solution. Interactions between the main system and perturbation create new patterns of behavior. It can be recognized when exact solutions are impossible, but approximations are useful. It helps interpret how small changes affect outcomes in a controlled way. Perturbation theory applies to physics, chemistry, and engineering. It influences predictions of energy levels, particle motion, and other system properties. Higher-order corrections often follow a predictable sequence. Repeated application improves accuracy and reveals regular trends in outcomes. It shows that complex systems can be understood by studying small changes. The method teaches us patience, careful observation, and step-by-step problem solving. Perturbation theory turns uncertainty into manageable understanding. The variational principle is a method used in physics and mathematics to find the state of a system that minimizes or maximizes a particular quantity. At its heart, it is about choosing the best path or configuration among many possibilities. Imagine a ball rolling down a hill. It naturally takes the path of least resistance. Similarly, the variational principle helps systems find an optimal solution. It relies on the idea that nature favors efficiency. Systems following this principle exhibit smooth changes and stable configurations. Components interact in a way that the total energy or action is minimized. This principle links motion, energy, and forces in a precise and predictable way. The structure involves defining a function called the action, which depends on the path or configuration of the system. All possible paths are considered, but only the one that makes the action smallest or largest is chosen. This creates a clear connection between cause and effect. Over time, systems evolve toward the configuration that satisfies the variational principle. Small changes in initial conditions lead to predictable adjustments. Interactions among parts of the system follow rules that minimize the overall action. One can recognize the variational principle in nature by observing patterns that conserve energy or maintain stability. Its interpretation depends on the system, whether mechanical, optical, or quantum. It applies to a wide range of systems, from a swinging pendulum to the motion of planets. Its influence extends to energy, forces, and the evolution of complex structures. Regularities appear as repetitive motions or equilibrium states. Predictable outcomes follow from the minimization or maximization of action. The variational principle shows that nature chooses the most efficient path. It guides scientific reasoning and offers a unifying idea across physics and mathematics. Identical particles are tiny objects that cannot be distinguished from one another even in principle. In physics, each particle of the same type shares exactly the same intrinsic properties, such as mass, charge, and spin. This means no label or mark can tell one particle from another. Their essence lies in the idea that swapping two identical particles does not produce a new physical state. These particles always have matching features. Electrons, for example, all have the same negative charge and the same mass. Identical particles exist as part of a larger group and show patterns that ordinary distinguishable objects do not. They follow specific rules that govern how they can occupy spaces and energy levels, creating links between one particle and another. Identical particles organize according to quantum laws. Fermions, like electrons, avoid being in the same state, while bosons, like photons, can gather in one state. This creates structured arrangements that explain stability in atoms and light behavior. The elements interact according to these patterns, forming predictable structures. The behavior of identical particles depends on their type. Fermions fill available spaces step by step, creating layers in atoms. Bosons can cluster, producing phenomena like lasers or superfluids. These patterns evolve consistently over time, shaping how matter and energy move. Scientists recognize identical particles through experiments and observations, noticing their unique patterns. Context matters, as their behavior can differ when grouped or isolated. They influence larger systems, from atoms to stars, affecting chemistry, electricity, and light. Their rules extend beyond a single particle to entire structures. Identical particles show repeated arrangements and tendencies. Electron shells, Bose-Einstein condensates, and photon beams are examples of predictable outcomes. Understanding identical particles teaches that order emerges from sameness. They reveal universal principles that guide nature at the smallest and largest scales. Fermions and bosons are two fundamental types of particles in the universe. Fermions, like electrons and protons, form the matter around us. Bosons, like photons, carry forces that make interactions possible. These particles shape the world in ways that are invisible yet powerful, creating patterns unlike anything we see in everyday life. Fermions follow a rule called the Pauli exclusion principle, meaning no two can occupy the same state. This gives them individuality. Bosons, on the other hand, like to gather in the same state, creating phenomena such as lasers and superfluids. Together, they show that the universe balances individuality and collectiveness in its tiniest elements. Fermions build atoms and molecules, which form matter. Bosons transmit forces, holding atoms together or moving energy. Their interactions create the structures we see, from stars to cells, and even influence the stability of planets and galaxies. Fermions can occupy distinct energy levels, changing when energy is added. Bosons can appear as waves or particles, shifting depending on the environment. Temperature, energy, and external forces can cause transformations that are visible in light, magnetism, and superconductivity. Bosons connect fermions through forces, and fermions arrange themselves to form matter. Their collective behavior can lead to surprising effects like condensation or electromagnetic fields, showing that small-scale rules create large-scale patterns. Understanding these particles allows us to build electronics, study stars, and even imagine quantum computers. They reveal rules that govern both the smallest and largest structures in the universe. Fermions and bosons are studied using experiments like particle accelerators and lasers. Their behavior changes depending on how they are measured, making observation both a challenge and a window into hidden laws. These particles teach that the universe follows deep, often counterintuitive rules. Questions about dark matter, superconductivity, and quantum entanglement continue to inspire curiosity and exploration. Fermi-Dirac statistics explains how particles called fermions, like electrons, behave in a system. Fermions follow a strict rule that no two can occupy the same state at the same time. This concept is mainly applied in quantum mechanics and solid-state physics. Unlike classical particles that can crowd together freely, fermions spread out according to this special rule. Fermions can be viewed through energy levels or spatial positions. They have both individual properties and collective behavior. One aspect focuses on occupation probability of energy states, while another emphasizes the distribution of many particles across those states. These aspects work together to define the overall structure of matter. Fermions interact with each other through exclusion. This interaction shapes the behavior of metals, semiconductors, and stars. The distribution of electrons affects electrical conductivity and thermal properties. Patterns like energy bands and Fermi surfaces emerge from these interactions. Fermions exist in distinct energy states. When temperature changes, the occupation of these states shifts. At absolute zero, all lowest states are filled, and higher states remain empty. Increasing temperature allows some fermions to move to higher energies. Electrons in atoms, metals, and molecules connect through energy distribution. Filling one state influences the availability of others. Collective behaviors, like conductivity and magnetism, arise from these linked states. Fermi-Dirac statistics helps explain metals, semiconductors, and white dwarfs. It is essential for electronics, nanotechnology, and astrophysics. It teaches how microscopic rules shape macroscopic phenomena. Scientists observe electron distributions using spectroscopy and other measurements. How electrons occupy energy levels explains conductivity and heat capacity. Observations reveal the patterns predicted by the statistics. This concept shows that simple rules at the particle level can create complex systems. It challenges classical intuition and opens questions about exotic materials and quantum technologies. Fermi-Dirac statistics connects the invisible world of electrons to the visible behavior of matter. Bose-Einstein statistics describes the behavior of particles called bosons. These particles can occupy the same energy state, unlike ordinary particles called fermions. The idea applies mainly to very small particles at extremely low temperatures. It departs from classical physics where particles are treated as distinct and separate. Instead, bosons show collective patterns that seem almost like a group acting as one. Bosons can be seen as individual particles or as part of a larger wave-like system. They show dual characteristics of being particles and waves. This duality allows them to create phenomena such as lasers or superfluids. The wave and particle aspects are connected, influencing how energy spreads and how the system evolves over time. In a system, bosons interact by sharing energy states. This interaction can lead to remarkable patterns, like condensation where many particles settle into a single state. Their behavior affects other particles and fields around them, producing ordered structures that emerge from simple rules. Bosons can exist in different energy levels. At very low temperatures, they can all collapse into the lowest energy state, forming a Bose-Einstein condensate. Changes in temperature or pressure transform the system and create shifts in how energy is distributed. Individual bosons connect through shared energy states. This leads to collective effects such as coherent motion or synchronized behavior. Small interactions between particles result in large-scale order that cannot be seen by looking at a single particle alone. Bose-Einstein statistics helps explain lasers, superconductivity, and superfluidity. It is important in quantum physics and technology. Understanding it shows how simple rules lead to complex behavior and helps predict system properties. The effects of bosons can be observed in experiments at very low temperatures. Measurements show condensation and wave-like behavior. Observation can even influence outcomes because the system is sensitive to changes. This concept challenges ideas of individuality and separation. It shows that collective behavior can dominate. Open questions remain about new states of matter and applications in quantum technology. Bose-Einstein statistics reveals deep patterns of nature hidden in the smallest scales. Bose-Einstein condensate is a state of matter formed when particles called bosons are cooled to temperatures near absolute zero. At this point, the particles move extremely slowly and begin to occupy the same space and energy state. Unlike ordinary matter, where each particle behaves individually, in this state, all particles act as a single quantum entity. The concept belongs to the field of quantum physics and challenges our usual understanding of how matter behaves. This state can be seen as both particle-like and wave-like. Individual atoms maintain their identity, yet they blend into a collective wave. Different characteristics coexist, such as superfluidity, where the condensate flows without friction, and coherence, where the particles are perfectly in sync. These aspects are deeply connected and emerge together because of the extreme cooling. Bose-Einstein condensate interacts with external fields and particles in unique ways. It can be influenced by magnetic or optical traps that shape its behavior. Its internal structure allows energy to move without resistance, which affects surrounding atoms and can create interference patterns. Patterns of movement emerge from these interactions. The condensate can change states if temperature or pressure varies. Heating slightly will break the condensate back into individual particles. Cooling forms the condensate and transitions it into a coherent quantum state. These transformations reveal the delicate balance of energy and motion. Individual atoms in the condensate are linked through quantum mechanics. Non-intuitive relationships appear, like all particles acting as one. Collective behaviors such as superfluid currents arise from these links. Understanding this condensate helps in quantum computing, precision measurements, and understanding the universe at low temperatures. It provides insights into complex systems where individual actions create unexpected collective results. Scientists observe the condensate using laser imaging and magnetic traps. Its behavior depends on how it is measured, revealing interference and flow patterns that are invisible in ordinary states. Bose-Einstein condensate challenges conventional ideas about matter. It opens questions about quantum mechanics and how macroscopic objects can exhibit quantum behavior. Exploring it teaches patience, precision, and wonder in science. Special relativity is a theory developed by Albert Einstein that explains how space and time behave when objects move very fast, close to the speed of light. It changes our usual understanding of time, distance, and motion. Unlike everyday experiences, events that seem simultaneous for one observer may not be simultaneous for another. This theory applies to objects moving at high speeds and is a foundation for modern physics. Time and space are not separate but connected in a four-dimensional framework called spacetime. Time can slow down for a moving object, while length can shrink along the direction of motion. Energy and mass are connected, meaning a moving object can gain more energy and behave as if it has more mass. These aspects coexist and influence each other, creating effects that are counterintuitive yet measurable. Special relativity affects how moving systems interact. A fast-moving spaceship experiences time differently from someone on Earth. Light signals, motion, and measurements all change depending on the observer's speed. Patterns such as time dilation and length contraction emerge from these interactions. Objects can be at rest or in motion. As speed increases, time slows and distances contract. Energy transforms into mass and vice versa, showing the fluidity of states in high-speed conditions. Changes occur smoothly but are significant at speeds near light. Events, observers, and measurements are linked through spacetime. Motion in one system affects the perception of time and space in another. The collective behavior of objects at high speeds follows predictable patterns from Einstein's equations. Special relativity is essential for GPS satellites, particle accelerators, and understanding the universe. It teaches that our everyday intuition about time and space does not always apply and helps explain high-energy physics and cosmic phenomena. Relativity is measured through precise clocks, light signals, and experiments. Observers moving relative to each other see different sequences of events. Observation affects interpretation, but does not change the physical laws themselves. Special relativity challenges common sense and expands human understanding of reality. It raises questions about the nature of time, space, and motion and continues to inspire exploration of deeper cosmic truths. Lorentz transformation is the set of mathematical rules that describe how space and time coordinates change for objects moving at high speeds, close to the speed of light. It belongs to the realm of special relativity and challenges the familiar ideas of absolute time and space. Unlike classical physics where time ticks the same for everyone, Lorentz transformation shows that time and distance are relative, depending on the observer's motion. This concept can be seen in terms of time dilation, where moving clocks run slower, and length contraction, where moving objects appear shorter. It also connects to the relativity of simultaneity, meaning two events happening at the same time for one observer may happen at different times for another. These perspectives coexist and are interlinked, giving a complete picture of how motion affects measurement. Lorentz transformation affects moving particles, light beams, and even measurements of energy and momentum. It changes how events are observed in different reference frames and influences interactions between objects moving at different speeds. Patterns emerge as observers see consistent laws of physics despite their motion. Objects can be at rest or moving at high speed. As they accelerate, time slows down, distances shrink, and events shift in sequence. These transformations evolve smoothly, following precise mathematical formulas. Time, space, and motion are deeply connected. Energy and momentum link with speed through Lorentz rules. Individual changes combine to produce consistent behavior across systems, showing hidden relationships in moving frames. Lorentz transformation is crucial in understanding particle physics, GPS satellites, and cosmic rays. It explains why high-speed travel affects time and why light speed is the ultimate limit. Its lessons extend to all areas where motion and observation matter. The effects are measurable with precise clocks and rulers. Observers in different frames experience events differently, but transformations predict these differences accurately. Observation itself becomes part of the physical description. Lorentz transformation changes our view of reality, showing time and space are flexible, not absolute. It challenges intuition and opens questions about faster-than-light travel and the nature of the universe. Relativistic energy and momentum describe how objects behave when they move close to the speed of light. Unlike normal energy and momentum, these quantities increase faster than we expect. The domain covers high-speed particles, cosmic rays, and objects in extreme conditions. It departs from everyday motion where mass and energy are simple and separate. Energy can appear as rest energy, kinetic energy, or total energy depending on viewpoint. Momentum depends on both mass and velocity, but changes at high speeds differently. These aspects coexist and combine in the energy-momentum relation, showing that energy and momentum are deeply linked. Relativistic energy interacts with forces, fields, and other particles. Collisions at high speed show unusual patterns, like creation of new particles. The energy-momentum relationship shapes how systems exchange energy and momentum, influencing outcomes in reactions and decays. Objects can be at rest, moving slowly, or near light speed. Interactions can transfer momentum, convert energy to mass, or produce radiation. Transitions follow precise rules that combine energy and momentum into one unified picture. Energy and momentum connect mass, velocity, and time. These connections explain phenomena like time dilation and mass increase. Small changes in one component can produce noticeable effects across the system. Understanding relativistic energy momentum helps in particle physics, astrophysics, and modern technology. It guides how we study cosmic events, accelerators, and even GPS satellites. The principle teaches the unity of energy and motion. We measure energy and momentum through experiments like particle collisions. Observers in different frames may see different values, highlighting relativity. Measurement influences interpretation of motion and energy transfer. This concept challenges classical ideas of separate mass and energy. It shows the universe behaves differently at extreme speeds. Open questions remain about how these principles connect to gravity and quantum systems. General relativity is a theory that explains how gravity works. Instead of seeing gravity as a force pulling objects, it describes gravity as the bending of space and time. Imagine space as a stretched fabric and objects, like stars and planets, as heavy balls that create dents in the fabric. This concept covers all large-scale systems in the universe. It challenges the familiar idea of gravity from everyday life, where we simply think of it as something that pulls objects down. Gravity can be seen as both a curve in space-time and as an influence on motion. Light, even though it has no mass, follows these curves. Matter and energy create these curves, while objects move along them. These perspectives coexist and explain phenomena such as planetary orbits and bending of light around stars. Massive objects affect the space around them, causing other objects to move along curved paths. This interaction shows patterns like the orbit of Earth around the Sun. The more mass an object has, the stronger the bending effect on spacetime. Spacetime can be stretched or compressed. Black holes are extreme states where spacetime is highly curved. Gravitational waves are changes rippling through spacetime caused by massive events like colliding stars. Gravity links distant objects. A supernova can influence nearby stars and planets. The universe behaves as a connected system where local changes can create far-reaching effects. This theory allows precise satellite navigation, prediction of black holes, and understanding the expansion of the universe. It shapes modern astrophysics and cosmology. We observe general relativity through effects like light bending, time slowing near massive objects, and gravitational waves. Observation depends on the position and motion of the observer. General relativity reveals that space and time are flexible. It challenges everyday intuition and opens questions about the universe, dark matter, and the nature of gravity itself. Curved spacetime is the idea that space and time are not flat, but bend and stretch around matter and energy. It describes how planets, stars, and light move not because of invisible forces, but because the surface they travel on is shaped. This concept comes from Einstein's theory of general relativity and extends beyond ordinary physics, showing the universe in a dynamic, flexible way. It challenges the familiar idea that space is a simple, empty stage where events happen. Spacetime can be seen as a smooth fabric, flexible and responsive. It can be shallowly curved near Earth or sharply curved near massive stars. Curvature affects how clocks tick and how light bends, showing the coexistence of time and space in one connected entity. The different curvatures influence each other, forming patterns of motion that are both predictable and surprising. Curved spacetime interacts with objects moving through it. Planets orbit because they follow the curves, not because they are pulled. Light bends when passing near massive objects. These interactions create the patterns of planetary motion and gravitational lensing, where distant stars appear shifted. Spacetime can be nearly flat, slightly curved, or extremely curved near black holes. Changes occur as mass or energy moves. Stars explode or collide, stretching spacetime and sending ripples known as gravitational waves that travel across the cosmos. Every object links to spacetime. A falling apple and orbiting planet both follow the curves created by nearby mass. Unexpected effects emerge, like time moving slower near strong gravity, showing the interconnected nature of all cosmic events. Understanding curved spacetime helps predict planetary motion, GPS accuracy, and black hole behavior. It reveals the universe as an active, interacting system and guides science in exploring extreme conditions beyond ordinary experience. Spacetime curvature is measured through the bending of light and timing of signals. Observers near massive objects see time differently from those far away. Interaction with spacetime shapes what can be observed. Curved spacetime changes how we view reality, showing that space and time are flexible and responsive. It raises questions about the beginning of the universe, black holes, and the limits of human understanding. Its study continues to inspire curiosity and exploration. Black holes are regions in space where gravity is extremely strong, so strong that nothing, not even light, can escape. They form when massive stars collapse under their own weight. This concept belongs to the realm of astrophysics and cosmology, exploring extremes of space, time, and matter. Black holes depart from familiar space objects like stars and planets because their gravitational pull creates a boundary called the event horizon, beyond which conventional physics breaks down. Black holes can be understood in different ways. Some are stellar black holes formed from dying stars, while supermassive black holes exist at the center of galaxies. They possess both an invisible, mysterious side and measurable effects on surrounding space. The bending of light, acceleration of nearby objects, and emission of X-rays show how these characteristics interact to reveal their presence. Black holes influence surrounding systems. They pull in gas, dust, and even stars, forming glowing accretion disks. Their gravity affects the orbits of nearby stars and bends light traveling close to them. Patterns such as jets of high-energy particles emerge from these interactions, linking black holes to the structure of galaxies. Black holes have different states depending on mass and spin. They can grow by absorbing matter or shrink through radiation. Transitions occur over millions of years, showing evolution from small stellar black holes to massive galactic centers. Black holes connect with other cosmic phenomena like neutron stars, galaxies, and gravitational waves. Their interactions are non-intuitive, yet they shape collective cosmic behavior, influencing galaxy formation and dynamics. Understanding black holes helps explain gravity, time dilation, and the life cycle of stars. They provide insights into extreme physics and test theories of relativity. Black holes are detected indirectly through X-rays, gravitational waves, and the movement of nearby objects. Observations depend on context and technology, showing that perception can alter understanding. Black holes challenge human imagination and scientific limits. They reveal mysteries about the universe, inspire curiosity, and leave open questions about what lies beyond the event horizon. Quantum field theory is the study of tiny particles and the fields that fill space. It explains how particles like electrons or photons exist and interact as ripples in invisible fields. Unlike everyday objects, these particles are not fixed things but patterns in a field that can appear or disappear. This theory applies to the smallest scales in the universe and goes beyond the usual ideas of solid objects or simple motion. A particle can be thought of as both a tiny point and a wave in a field. Fields can carry energy in different ways, and particles can appear as excitations of these fields. The wave and particle perspectives coexist and are linked through the rules of quantum physics. Understanding one aspect helps to understand the other. Fields interact with each other and with particles. A photon field can influence an electron field, causing changes in energy or motion. These interactions create patterns that can be predicted, such as forces or particle collisions, showing how individual components affect the whole system. Fields can exist in various states, such as calm or excited. Particles can appear or vanish depending on energy conditions. Transitions between states explain processes like light emission or particle decay. Different fields are connected. Changes in one field can create effects in another. Complex behaviors emerge when many fields interact, producing the particles and forces we observe. Quantum field theory helps explain atomic structure, particle physics, and the early universe. It is essential in technology such as semiconductors and lasers, and provides insight into the building blocks of reality. Particles and fields are measured indirectly through experiments like particle collisions or radiation detection. Observation can influence outcomes, showing the delicate link between measurement and reality. Quantum field theory challenges ordinary views of matter and space. It raises questions about the nature of reality and what we may yet discover about the universe. It invites curiosity and deeper exploration of the unseen forces that shape everything. Lagrangian mechanics is a way to describe motion using energy instead of forces. It focuses on the difference between kinetic energy and potential energy. This approach applies to objects moving in simple paths or in complex systems with many parts. Unlike Newtonian mechanics, it does not always rely on vectors or direct forces. The concept can be seen as a balance between motion and position. It can also be interpreted as a tool for predicting future movement. The kinetic energy aspect shows how fast something moves, while potential energy shows the effect of position. Together, these aspects form a complete view of system behavior. In a system, the Lagrangian interacts with all moving parts. It considers constraints, like ropes or rails, and determines how these limits affect motion. Patterns emerge naturally, showing smooth or oscillating movements depending on the energies involved. A system can be at rest, moving steadily, or accelerating. Energy changes lead to transformations, like a pendulum swinging higher or lower. Transitions follow clear rules, where total energy influences the path taken. Each component's motion affects the others through forces or constraints. Hidden relationships appear, such as synchronized motion in linked pendulums. The collective movement can be very different from individual motion. Lagrangian mechanics helps in robotics, space travel, and physics simulations. It provides a general tool for analyzing complex systems. By understanding energy relationships, engineers and scientists can design more efficient machines. The concept is observed through motion and energy measurement. Perspective matters, as the same system may look different in rotating frames. Observing energy changes reveals underlying rules of motion. This method broadens understanding beyond forces. It challenges simple ideas about motion and opens paths to quantum mechanics and modern physics. Questions remain about optimal ways to apply it to very large or tiny systems. Hamiltonian mechanics script. Hamiltonian mechanics is a way to describe motion in physics using energy instead of force. It focuses on two main quantities, called position and momentum, which together define the state of a system. Unlike Newtonian mechanics, that emphasizes forces and accelerations, Hamiltonian mechanics studies how energy flows and changes over time in a system. It applies to particles, planets, and even complex systems like molecules. This concept can be viewed as a map of motion. One aspect is the energy landscape, where higher points represent more energy. Another aspect is the phase space, where each point shows a system's position and momentum. Both aspects coexist, offering different insights, and understanding one helps interpret the other. They work together to show the system's behavior fully. Hamiltonian mechanics describes how a system interacts with itself and the environment. Internal interactions are seen as energy changes between components. External influences, like forces or fields, change the system's energy and motion. Patterns emerge as predictable paths called trajectories in phase space. The system can be in different states depending on its energy and momentum. When energy is added or removed, the system transitions to a new state. Over time, these transformations follow clear rules defined by the Hamiltonian equations. Different parts of a system are linked through energy. A change in one component affects others. Collective motion emerges from these interactions, showing the whole system behaves as more than just the sum of parts. Hamiltonian mechanics helps predict motion in physics, astronomy, and engineering. It provides insight into stability, energy conservation, and dynamics of complex systems. Learning it allows understanding of patterns across different physical phenomena. The Hamiltonian can be measured by observing position and momentum. How we look at the system affects predictions and understanding. Careful measurement helps track trajectories accurately. Hamiltonian mechanics shows energy as a central principle in nature. It challenges simple cause and effect thinking and opens questions about chaos, quantum systems, and unexplored dynamics. It teaches that motion and energy are deeply connected across all systems. Noether's theorem is about the deep connection between symmetry and conservation laws in physics. At its essence, it says that every symmetry of nature leads to something that stays constant. For example, if the laws of physics do not change over time, energy is conserved. Its domain covers mechanics, fields, and the foundations of modern physics. Unlike ordinary rules that describe only forces or motion, this theorem links abstract patterns to real, measurable quantities. The theorem can be seen in different ways. One way is through space, where symmetry in position leads to conservation of momentum. Another is through time, where time symmetry ensures energy remains constant. These aspects coexist, showing that changing one part of a system might still preserve certain overall quantities. They are interrelated, forming a web where symmetries guide physical outcomes. Noether's theorem interacts with all parts of a physical system. It influences the motion of objects, the flow of energy, and the behavior of forces. When applied to a system, patterns emerge, such as repeated motion or predictable energy distribution. Internal changes and external forces reveal these patterns clearly. A system can be at rest, moving, or oscillating. When interactions occur, like collisions or rotations, conserved quantities remain the same. The system transitions smoothly between states while following these underlying rules. Different subsystems are connected through conserved quantities. Energy in one part affects momentum in another. Some links are hidden but emerge when the system evolves, showing collective behavior shaped by symmetry. This theorem explains why energy, momentum, and angular momentum are conserved. It guides engineers, physicists, and astronomers. Understanding it helps predict behavior in complex systems and reveals universal principles. The theorem can be recognized by looking for symmetry. Measuring energy or momentum confirms it. Observing changes in one part while others remain constant highlights its effect. Noether's theorem connects abstract ideas to real-world outcomes. It challenges simple cause and effect thinking. Many areas remain unexplored, including quantum fields and cosmology, making it a doorway to deeper understanding. Gauge symmetry is a principle in physics that describes how certain properties of a system remain unchanged even when we make specific transformations. It helps us understand forces, like electromagnetism, weak and strong nuclear forces. Unlike ordinary symmetries we see in daily life, gauge symmetry works in a more abstract, mathematical way and shapes the rules of particle interactions. Gauge symmetry can be seen from different angles. One perspective is mathematical, using equations to describe invariance. Another is physical, showing how particles interact without changing the overall system. These perspectives coexist, and together they reveal deeper connections between forces and fields in nature. In a system, gauge symmetry controls how particles and forces interact. For example, it ensures that electric charge is conserved in electromagnetic interactions. The symmetry influences both internal dynamics of a system and its effects on the surrounding environment, creating predictable patterns in particle behavior. Systems with gauge symmetry can exist in multiple states or configurations. Changing the gauge can transform the appearance of the system without altering physical outcomes. This shows how systems can evolve or transition while keeping core properties intact. Gauge symmetry links separate parts of a system, creating hidden connections. Individual particles obey the same rules, leading to collective behaviors that would not appear from a single component alone. These emergent relationships are crucial in understanding complex interactions. Gauge symmetry is key to modern physics, forming the foundation of quantum field theories. It helps predict particle interactions, design experiments, and explore new physics. The concept shows how abstract rules have broad significance in explaining natural laws. Though abstract, gauge symmetry can be detected through experiments and measurements, such as particle accelerators. Observing how transformations leave systems unchanged helps scientists interpret underlying principles. Gauge symmetry challenges everyday intuition and highlights hidden order in nature. It raises questions about unifying forces and inspires curiosity about the fundamental structure of the universe. Its exploration continues to expand human understanding of reality. The Standard Model is the framework that explains the building blocks of matter and the forces that act between them. It focuses on particles like quarks, electrons, and neutrinos, along with forces such as electromagnetism, the weak force, and the strong force. This model moves beyond everyday experience by showing that everything around us is made of tiny, invisible particles and interactions that follow strict rules. The Standard Model can be viewed as a map of particles and forces. Particles can act as matter or energy carriers depending on context. Forces like electromagnetism and the strong force have different effects but work together to shape matter. These aspects are connected, forming a network where one particle or force influences others in complex ways. Particles interact through the forces predicted by the Standard Model. Quarks bind together to form protons and neutrons, while electrons orbit around nuclei due to electromagnetic forces. These interactions create patterns in atoms and molecules that build stars, planets, and life. Particles can exist in different states and change through interactions. For example, unstable particles decay into lighter particles, while energy can transform into matter in collisions. These transitions show how the universe evolves on a fundamental level. The Standard Model shows relationships between distant elements, such as how forces affect particles across space. Collective behaviors emerge when many particles interact, like in the formation of a crystal or a star, revealing hidden order. It helps scientists understand nuclear reactions, particle accelerators, and the early universe. The model guides research in physics, chemistry, and cosmology, showing universal principles of matter and energy. We study particles using experiments like collisions and accelerators. Observing patterns helps us measure properties such as mass, charge, and spin. Observation shapes how we understand the universe at the smallest scales. The Standard Model challenges familiar ideas of matter, showing an invisible world governed by rules. Questions remain about dark matter and gravity, inviting further exploration and expanding the limits of human knowledge. Renormalization is a method used in physics and mathematics to make sense of quantities that seem infinite or undefined. It focuses on understanding how small-scale details affect large-scale behavior. The scope includes fields like quantum physics, statistical mechanics, and complex systems. Unlike usual calculations where numbers behave normally, renormalization deals with adjusting or redefining values to reveal meaningful patterns. Renormalization can be seen as a process, a tool, or a way of thinking. One perspective treats it as a way to remove infinities and simplify equations. Another considers it as a bridge between microscopic interactions and macroscopic effects. These viewpoints coexist and complement each other, showing how small parts influence the overall system. Within a system, renormalization identifies which interactions matter at different scales. It influences how particles, forces, or variables behave collectively. Patterns emerge as the system organizes itself, showing predictable behavior despite underlying complexity. Systems can exist in various states like solid, liquid, or critical points. Renormalization tracks how these states change when conditions vary, such as temperature or energy. It explains transitions and how small changes can produce large effects over time. Renormalization uncovers hidden links between separate elements. Microscopic actions can generate unexpected macroscopic behavior. Understanding these linkages helps explain why collective properties appear even when individual components seem random. Renormalization has practical applications in physics, chemistry, and even finance. It helps predict outcomes in complex systems and offers general principles for scaling and simplification. Its utility lies in revealing order from apparent chaos. The concept can be observed through experiments or simulations. How we measure and interpret interactions affects the understanding of the system. The perspective taken can change the conclusions drawn about the behavior of elements. Renormalization challenges conventional notions of infinity and scale. It shows the deep connection between small and large structures and opens questions about unexplored phenomena. It invites curiosity about hidden order in nature. Quantum gravity explores how gravity works when we look very closely at the smallest pieces of the universe. It tries to combine the ideas of quantum mechanics, which governs tiny particles, with Einstein's theory of gravity, which explains planets and stars. Unlike familiar physics, space and time themselves may behave like something flexible or grainy at the tiniest scale. Quantum gravity can be thought of in different ways. One approach imagines space as a network of tiny loops, another sees it as vibrating strings. Both describe the same reality, but from different angles. These perspectives interact, offering hints about how time, space, and matter connect deeply. Within a system, quantum gravity affects particles, energy, and spacetime itself. Small fluctuations can influence larger structures, like galaxies or black holes. Patterns emerge where quantum effects shape the overall behavior of the universe in ways that are subtle but profound. Space and time might exist in multiple forms, sometimes smooth and sometimes jagged. Under extreme conditions, like near a black hole, these forms transform, showing new rules. These transformations help explain how the universe evolves from the very small to the very large. Quantum gravity links tiny particles with cosmic structures. Unexpected connections appear, such as the way entangled particles might reflect spacetime geometry. The behavior of one part can influence distant regions, showing the universe is connected in surprising ways. Understanding quantum gravity could explain the birth of the universe, or what happens inside black holes. It offers principles to unite all forces in nature, helping us understand complex systems across science. Quantum gravity is observed indirectly through particle collisions, gravitational waves, or cosmic radiation. Our perspective changes how we interpret these signals, showing the role of measurement in shaping what we know. Quantum gravity challenges what we know about reality. It asks if space and time are fundamental or emergent. Many questions remain, inviting curiosity and imagination to explore the unseen foundations of the universe.